7 miles beneath the Pacific Ocean, the pressure is so extreme that human bone dissolves. The water is pitch black. The temperature hovers just above freezing, and somehow, life thrives there. The Mariana Trench is the deepest scar on Earth. Inside it, you will find creatures with transparent skulls, vents that spit liquid sulfur, and a pool of molten rock found nowhere else on this planet. If you enjoy this journey, hit like and subscribe. Now take a breath. We are going down. Most people think they understand the ocean. They picture sandy beaches, waves rolling in, maybe dolphins jumping through blue water. And that picture is real. It just only covers the top layer of a world that goes down for miles. The part of the ocean that gets sunlight, the part where coral reefs grow and sea turtles swim, only reaches down about 660 feet. That is where almost all marine life lives. Below that, things start to change fast. At around 850 feet, you have passed the depth where military submarines operate. Sunlight is already fading here. The water gets colder. Colors start to disappear. Red vanishes first, then orange, then yellow. The deeper you go, the more the ocean swallows light, until there is nothing left to see. By the time you reach 3,300 feet, you have entered a zone called the Midnight Zone. No light from above will ever touch you again. From this point forward, the only glow comes from living, creatures that make their own, and most of the ocean sits below this line. Here is a number that should bother you. The average depth of all the world's oceans is about 12,100 feet. That is over 2 miles straight down. And that is just the average. There are places far, far deeper. The wreck of the Titanic sits at about 12,500 feet. That is considered deep by most standards. Reaching it requires specialized submersibles. The pressure at the Titanic is around 400 times what you feel standing at sea level. It took decades before technology existed to visit it, and the Titanic is nowhere close to the bottom. Below 12,000 feet, you enter what scientists call the abyssal zone. Temperatures hover just above freezing. Food is scarce. The animals here look like they belong on another planet. Some have no eyes. Others have enormous mouths, designed to eat whatever drifts down from above, because meals this deep are rare. Life here survives on scraps. But even the abyssal zone has a flaw, and beneath that flaw, the earth cracks open into trenches. Deep, narrow gashes in the ocean crust where the pressure is so extreme that it crushes steel. Where water weighs so much that it changes how chemistry works. Where bones would dissolve. The deepest of all these trenches has a name. It is called the Mariana Trench. And it drops to a place so far down that if you put Mount Everest at the bottom, the peak would still be over 7,000 feet underwater. Think about that. The tallest mountain on Earth, fully submerged, and you would still need to swim more than a mile just to reach the top. At this depth, you are nearly 7 miles below the waves. The pressure is over 1,000 times what you feel at sea level. That is roughly 16,000 pounds pressing on every square inch of your body. The equivalent of 50 jumbo jets stacked on top of one person. And yet, something lives there. Scientists confirmed this decades ago, and they keep finding more. Every expedition to the trench comes back with evidence that life found a way into the most extreme environment on our planet. Creatures that should not exist, according to basic biology, are thriving in pitch black water at freezing temperatures under pressures that would flatten a car. We have explored less of the deep ocean than we have of the moon. We have sent more people into outer space than to the bottom of the Mariana Trench. The deepest place on Earth is also the most mysterious, and what scientists recently uncovered about its true, terrifying scale changes everything we thought we knew. But before we can go down, we need to understand what tore this trench open in the first place. The Mariana Trench did not appear overnight. It was not carved by water or worn down by time. It was ripped open by a force so powerful that it has been reshaping the planet for hundreds of millions of years. And it is still happening right now, beneath the Pacific Ocean, as you listen to this. Deep under the ocean floor, the Earth is made up of massive slabs of rock called tectonic plates. These plates are not sitting still. They are constantly moving, sliding over a layer of hot, partially melted rock below them. Most of the time, this movement is slow, a few inches per year. You would never feel it. But when two of these plates collide, something violent happens. In the western Pacific Ocean, about 200 miles east of a small chain of islands called the Mariana Islands, two enormous plates are crashing into each other. The Pacific Plate, one of the largest slabs of rock on Earth, is pushing westward, and it is colliding head-on with the smaller Mariana Plate. When these two meet, one of them has to give. The Pacific Plate is older, much older. The rock along its western edge has been traveling across the ocean floor for around 170 million years. That makes it some of the oldest oceanic crust on the planet. And because it has been cooling for so long, it is heavier and denser than the younger Mariana Plate, so it sinks. The Pacific Plate dives beneath the Mariana Plate in a process scientists call subduction. Picture a massive sheet of rock slowly bending downward and plunging into the Earth like a conveyor belt heading underground. The movement is relentless. It has been happening for tens of millions of years, and it will not stop anytime soon. As the heavy plate descends, it drags the ocean floor down with it, pulling the crust into a long, deep trench at the point where the two plates meet. The deeper the plate sinks, the deeper the trench becomes. That trench is the Mariana Trench. It stretches for over 1,580 miles across the Pacific Ocean floor. That is longer than the distance from Los Angeles to Dallas. Its average width is 43 miles, though in some places it narrows into tight canyons. And at its deepest point, a small valley called Challenger Deep, it plunges nearly 7 miles below sea level. This is confirmed science. Geologists have measured it, mapped it, and studied it for over a century. But here is what makes it unsettling. The collision is not over. The Pacific Plate is still moving, still sinking. Every year, it pushes a little further beneath the Mariana Plate, and the trench adjusts. This is an active subduction zone, one of the most powerful geological boundaries on Earth. It produces earthquakes. It feeds volcanic eruptions. The chain of volcanic islands that make up the Mariana Islands exists because of this exact process. As the sinking plate descends deep enough, parts of it melt, and that molten rock rises back up to form volcanoes. So the same force that created the deepest place on Earth also built the islands that sit above it. Destruction and creation happening at the same boundary. The trench is shaped like a crescent, curving gently across the ocean floor like a scar. From above, if you could drain the Pacific, it would look like a massive wound in the Earth, a canyon so deep and narrow it seems impossible. Scientists often describe it as one of the most extreme geological features on the planet, and we barely knew it existed until a small ship dragged a weighted rope through the water 150 years ago. That story starts with a crew of British sailors, a ship called Challenger, and a discovery that would change how we see our own planet. In December of 1872, a British warship named HMS Challenger left the harbour at Portsmouth, England. It had been stripped of most of its cannons and refitted with scientific equipment, rope, thermometers, and dredging gear. Its mission was unlike anything attempted before. The ship was going to travel the world and measure the ocean. For the next 3.5 years, the Challenger sailed nearly 70,000 miles across every ocean on Earth. The crew dropped weighted ropes into the water again and again, measuring how deep the seafloor sat at hundreds of different points. They pulled up samples of mud, rock, and strange creatures from depths no one had ever reached. It was slow, exhausting work. The crew lowered heavy lines by hand, waited for them to hit bottom, then hauled them back up. Every sounding took hours. Conditions on the ship were harsh. Many sailors deserted along the way. Some died. But on March 23, 1875, the expedition made a measurement that stunned everyone on board. They were sailing through the western Pacific Ocean, near a small chain of islands east of the Philippines. When the weighted line was lowered over the side, it kept going, and going. It did not hit anything for a very long time. When it finally stopped, the reading came back at 4,475 fathoms. That is roughly 26,850 feet, over 5 miles. The crew had never recorded anything close to that depth. No one on Earth had. They had just discovered the deepest known point in the ocean, though they did not yet realize how much deeper it actually went. Their measurement was limited by the technology of the time. A weighted rope, stretching through miles of ocean current, was far from precise, but it was enough to mark the spot. The area was labeled on their charts. They called it the Challenger Deep, after the ship itself. It took decades for anyone to return. In 1951, another British ship, this one also named Challenger, came back to the area. HMS Challenger II was conducting a new survey of the Pacific, and the crew decided to revisit the trench their predecessor had found 76 years earlier. This time, they had better tools. Echo sounders could bounce sound waves off the ocean floor and calculate depth from the time it took for the signal to return. But even those instruments were not powerful enough to reach the bottom of Challenger Deep on the first attempt. The sound took so long to travel down and back that the equipment could not record it. So the crew improvised. They attached 140 pounds of scrap iron to a wire and lowered it over the side. It took an hour and a half for the weight to reach the bottom. The depth they measured was staggering, over 35,000 feet, nearly 7 miles. The trench was far deeper than anyone in 1875 had realized. This was the moment scientists understood that the ocean contained a place more extreme than they had imagined. A canyon deeper than any mountain is tall. A place where the pressure, the cold, and the darkness would test the limits of anything sent into it. But measuring it from above was one thing. Going there was something else entirely. For years after that survey, Challenger Deep sat on maps as a number, a depth reading. Nobody had the technology to actually reach it. No submersible on Earth could survive the pressure. No camera could function in the darkness at that depth. The trench was known, mapped, and completely unreachable. That changed on January 23rd, 1960, when 2 men climbed inside a metal sphere and dropped into the abyss. What they experienced on the way down was terrifying. And what they found at the bottom rewrote everything scientists believed about life on Earth. After HMS Challenger measured the trench in 1875, the world knew the ocean was deeper than anyone had guessed. But knowing the depth and actually reaching it were 2 completely different problems. For 85 years, no human could get there. The issue was pressure. For every 33 feet you descend in the ocean, the pressure increases by 1 atmosphere. At sea level, you feel 1 atmosphere of pressure. That is about 14.7 pounds per square inch. Normal. Comfortable. Your body is built for it. At the bottom of the Mariana Trench, the pressure is over 1,070 atmospheres. That translates to roughly 16,000 pounds of force on every square inch. To build something that could survive that kind of crushing weight, engineers needed materials and designs that simply did not exist for most of the 20th century. Standard submarines could not come close. Military submarines operate at around 800 to 1,000 feet. Some can push to about 2,000. The deepest rated military submarine ever built could reach around 3,000 feet. The Mariana Trench is over 36,000. The gap between what existed and what was needed was enormous. The first real attempt to go deep came from a father and son team in Switzerland. Auguste Piccard, a physicist, designed a new kind of vessel called a bathyscaphe. Think of it as an underwater balloon, but in reverse. Instead of rising with hot air, it sank using heavy iron pellets for weight, and used a float tank filled with gasoline, which is lighter than water, to control buoyancy. His son, Jacques Picard, helped refine the design and became the pilot. The vessel they built was called the Trieste. It was not graceful. It was a bulky machine with a small steel sphere at the bottom just big enough for 2 people to sit inside. The walls of that sphere were 5 inches thick, designed to withstand forces that would crush anything thinner. The United States Navy became interested in the project and purchased the Trieste. They saw its potential for deep ocean research and military intelligence. After years of testing and modifications, the Navy approved a mission to the deepest point in the ocean. On January 23, 1960, Jacques Picard and United States Navy Lieutenant Don Walsh climbed into the Trieste at the ocean's edge near Guam. The sphere was cramped. There were no comfortable seats. Instruments lined every wall. A single small porthole allowed them to look outside. The descent took nearly 5 hours. 5 hours of sinking through blackness, watching the pressure gauges climb, listening to the hull groan as the water squeezed tighter and tighter around them. At one point, a loud crack echoed through the cabin. The outer window of the entry tunnel had cracked under the pressure. Both men paused, waiting to see if the vessel would hold. It held. They kept going. When they finally reached the bottom of Challenger Deep, the instruments read 35,814 feet, nearly 7 miles below the waves. No human had ever been this deep. No human would return for over half a century. They spent only 20 minutes on the floor. Their landing had stirred up a thick cloud of sediment, making it nearly impossible to see through the porthole. The water was murky, dark, and featureless. But in those 20 minutes, Walsh and Picard saw something that changed science forever. Through the clouded porthole, they spotted what appeared to be a flat, pale fish lying on the bottom. A living creature at a depth where scientists had confidently declared nothing could survive. Life, it turned out, had beaten us to the bottom. The journey back up took over 3 hours. When the Trieste reached the top, the 2 men emerged to a world that now knew the deepest place on Earth was not empty. And then, incredibly, nobody went back. Jacques Picard and Don Walsh reached Challenger Deep on January 23, 1960. They touched the deepest point on the planet. They saw life where science said there should be none. And when they returned to the top, the world celebrated. Then the world moved on. The details of what happened during those 20 minutes on the bottom are often glossed over. People know the dive happened. They know it set a record. But the actual experience of being nearly 7 miles underwater, inside a metal sphere barely big enough for 2 grown men, is rarely described in full. The descent started in the early morning hours near Guam. The ocean was rough that day. Waves battered the Trieste as crew members prepared the vessel. Picard and Walsh squeezed through a narrow tunnel and into the observation sphere at the bottom of the craft. Once sealed inside, there was no getting out until the mission was over. The sphere was small, roughly 6.5 feet across inside. 2 men, shoulder to shoulder, surrounded by dials, gauges, and switches. Temperature inside was cold. There was no heating system. Condensation dripped from the walls as they descended through warmer water into freezing darkness. For the first hour, light from above still filtered down, faint, blue, dimming with every minute. Then it was gone. Total blackness swallowed everything outside the porthole. The only light came from the Trieste's external lamps, which could barely cut through the water. The sounds were constant. Creaking, groaning, tiny pops and shifts as the pressure mounted. Every noise felt like a warning. The hull was being compressed from all sides by a force that grew stronger with every foot of descent. At 20,000 feet, the pressure outside was already over 600 times what it is at sea level. Then, at around 32,000 feet, the crack happened. A loud, sharp bang echoed through the cabin. Both men froze. Picard later described the moment as one of the most frightening of his life. Something in the entry tunnel above the sphere had given way. They had no way to inspect it, no way to fix it. If the sphere itself was compromised, the ocean would crush them instantly. They waited, checked instruments, listened for any sound of water leaking in. Nothing. The sphere was intact. The crack had come from the outer window of the access tunnel, which was not part of the pressure chamber. It was damaged, but the critical structure had held. They decided to continue. When the Trieste finally touched the ocean floor at 35,814 feet, the landing kicked up a massive cloud of fine, white sediment. It billowed up around the vessel like underwater fog, blocking the porthole almost completely. For several minutes, Picard and Walsh could see almost nothing. Just a thick, swirling haze lit faintly by their external lights. Then, slowly, as some of the sediment began to settle, Picard pressed his face to the glass. He saw the bottom, flat, pale, featureless. A desert of fine silt stretching into darkness. And then he saw movement. Something flat and pale, about a foot long, drifted across the seafloor near the porthole. Picard described it as resembling a flatfish, possibly a sole. A vertebrate with eyes, moving deliberately along the bottom of the deepest place on Earth. Scientists at the time were skeptical. Some argued it could have been a sea cucumber or another invertebrate, not a true fish. The debate has never been fully settled because no photographs were taken. The sediment cloud made cameras useless, but the observation mattered enormously. Confirmed or debated, it suggested that complex life could exist under pressures that were thought to be lethal to anything with a skeleton. After 20 minutes, Picard and Walsh released the iron ballast and began the long ascent. The journey up took 3 hours and 17 minutes. When they broke through to open air, they had completed the deepest dive in human history. And nobody would match it for 52 years. The reason for that gap is almost as strange as the dive itself. Picard and Walsh reached the bottom in 1960. The next human to visit Challenger Deep did not arrive until 2012. For 52 years, the deepest place on Earth sat empty of human presence. Unmanned probes visited occasionally. Sonar scans mapped the terrain from above, but no person went back. The question is simple. Why? The answer is complicated, and it says more about us than it does about the trench. Part of the reason was cost. The Trieste mission was funded by the United States Navy, and it was expensive. Building and operating a vessel that could survive the bottom of the ocean required specialized materials, years of engineering, and massive logistical support. After the dive succeeded, the Navy had proven it could be done. The scientific value of sending humans back was debated. Why risk lives and spend millions when unmanned vehicles could collect samples and take pictures? Another part of the reason was the space race. In 1960, the same year Picard and Walsh reached the ocean floor, the Cold War was in full swing. The United States and the Soviet Union were locked in competition, and the battlefield had shifted upward. Space became the priority. Funding, public attention, and political willpower all pointed toward the sky. Within a decade, humans walked on the moon. The ocean, meanwhile, fell off the radar. It is one of the strangest facts in exploration history. We chose to look up instead of down. And while we launched satellites, built space stations, and sent robots to Mars, the deepest point on our own planet sat unvisited. During those 52 years, technology for deep-sea exploration did advance. Remotely operated vehicles became smaller, smarter, and more capable. In 1995, a Japanese robotic probe called Kaiko reached the bottom of Challenger Deep and sent back footage. It confirmed that life existed there, capturing images of tiny organisms in the sediment. But Kaiko was a machine. It could not describe what it felt like. It could not look around with human curiosity and decide, on a whim, to investigate something strange. Several other unmanned expeditions followed. Each brought back data, sediment samples, temperature readings, sonar images of the trench walls. Scientists learned more about the geology and chemistry of the deep, piece by piece, but the human element was missing. Then, in 2012, someone decided to change that. James Cameron, the filmmaker behind Titanic and Avatar, had spent years quietly developing a submersible designed specifically for a solo dive to Challenger Deep. The vessel was called the Deep Sea Challenger. It was a vertical torpedo, 24 feet tall, built from a special type of foam that could withstand extreme pressure. At the bottom, a single pilot compartment held one person in a steel sphere just over 43 inches wide. On March 26, 2012, Cameron climbed inside and descended alone. The dive took 2 hours and 36 minutes. When he reached the bottom, he spent about 3 hours exploring the seafloor, using cameras and mechanical arms to collect samples. He described the landscape as barren and alien, a vast, empty plain of sediment with almost no visible life. It was, in his words, completely desolate, but the dive was not smooth. His batteries drained faster than expected. Sonar systems failed. Thrusters malfunctioned, making it hard to steer. The trench was actively fighting his equipment, as though the pressure was slowly disabling every system on the vessel. Cameron made it back safely, but he later admitted the dive was more dangerous than he had expected. The trench had humbled him completely. Still, his mission proved something truly important. A single person, with enough determination and resources, could reach the very bottom of the world. And that opened the door for what came next. Because in 2019, another explorer went even deeper. And what he found at the bottom was both amazing and heartbreaking. When James Cameron reached the floor of Challenger Deep in 2012, he became only the third person in history to see the bottom of the Mariana Trench with his own eyes. 52 years had passed since Piccard and Walsh made their descent. Technology had advanced enormously. Expectations were high. What Cameron found was silence. The Deep-Sea Challenger landed on a flat, featureless plain of pale sediment. The cameras mounted on the outside of the vessel captured an endless stretch of soft, off-white silt that looked more like the surface of the moon than the bottom of an ocean. There were no towering rock formations, no dramatic canyons, no thriving ecosystems visible from the landing spot. Cameron later described it as the most desolate place he had ever seen. Alien was the word he kept using. A place so removed from anything familiar that it felt like visiting another planet. But desolate does not mean dead. During his 3 hours on the bottom, Cameron observed small signs of life. Tiny organisms drifting near the sediment. Faint tracks in the silt where something had crawled. The seafloor was not lifeless, but the creatures living there were small, sparse, and ghostly. Nothing jumped out at the cameras. Nothing swam past in dramatic fashion. The life at the very bottom of the trench was subtle, quiet, almost invisible. This makes sense when you consider what is happening down there. At nearly 36,000 feet, the pressure is crushing. The water temperature sits between 34 and 39 degrees. No light reaches this depth, no plants grow. The only food source is what scientists call marine snow, a constant slow rain of dead organic matter drifting down from the upper ocean. Tiny flakes of dead plankton, fish waste, and decomposing material that can take weeks to sink from the sunlit zone to the trench floor. Imagine living in a world where your entire food supply arrives as a faint shower of dust from 7 miles above you. That is what creatures at the bottom of Challenger Deep depend on. Cameron's submersible also had problems that limited what he could explore. The hydraulic fluid in one of his mechanical arms leaked within minutes of landing. His horizontal thrusters partially failed, making it difficult to move across the bottom. And his sonar cut out entirely, leaving him unable to map the terrain ahead. He was essentially sitting on the ocean floor in a cramped sphere with failing equipment, surrounded by total darkness. 7 miles from the nearest air. The trench was not cooperating. Despite the technical failures, the footage Cameron brought back was valuable. Scientists studied the sediment samples and video for years. They confirmed microbial life in the silt and documented the types of geological formations visible on the trench floor. The data helped fill in gaps that 52 years of unmanned probes had missed. But perhaps the most important thing Cameron brought back was a feeling, a description. He told the world what it was actually like to sit at the deepest point on Earth, the loneliness of it, the eerie stillness, the sense that you are farther from other humans than almost anywhere else on the planet. At the bottom of Challenger Deep, you're more isolated than an astronaut on the International Space Station. The station orbits only about 250 miles above Earth. Challenger Deep is nearly 7 miles down, surrounded by water that would kill you instantly if your vessel failed. Cameron called it humbling. He said the trench made him feel small in a way that nothing else in his life had. And he raised a question that scientists are still trying to answer. If the bottom of Challenger Deep looked that barren, where was all the life that probes had detected in other parts of the trench? Were there deeper valleys, hidden canyons, or thermal vents nearby that hosted richer ecosystems? Was Cameron's landing site simply the wrong spot? The answer, it turns out, is yes. The trench is not one uniform environment. It contains worlds within worlds, and reaching those hidden places would require someone willing to go back, again and again. Before we go deeper into the trench, you need to understand what would happen to you if you were there without protection. Because the Mariana Trench does not just kill you, it erases you. At sea level, the atmosphere pushes on your body with about 14.7 pounds of force per square inch. You do not feel it because your body pushes back with the same amount of pressure. Everything is balanced. That is why you can breathe, move, and function normally. Now picture yourself descending into the ocean. For every 33 feet you go down, the pressure increases by 1 atmosphere. At 33 feet, the pressure has doubled. At 66 feet, it has tripled. This happens smoothly, steadily, and relentlessly. Recreational divers usually stay above 130 feet. At that depth, the pressure is already about 4 times what it is at sea level. Go deeper without proper training and equipment, and your body starts to rebel. Nitrogen in your blood begins to act like a drug, causing confusion, poor judgment, and hallucinations. Divers call it the rapture of the deep. At 600 feet, even with specialized gas mixtures and diving gear, the human body is at its limits. The deepest recorded scuba dive in history reached just over 1,000 feet. That diver spent years training for it and needed over 13 hours of decompression stops on the way back up. The bottom of the Mariana Trench is 36,000 feet, 36 times deeper than the deepest scuba dive ever achieved. At that depth, the water column above you weighs enough to create a pressure of over 16,000 pounds per square inch. That is more than 1,000 times what you feel standing on a sidewalk. Scientists sometimes describe it as the weight of about 50 jumbo jets concentrated on a single person. If an unprotected human body were somehow placed at the bottom of Challenger Deep, the destruction would be instant and total. Every air-filled space in your body would collapse. Your lungs would crush inward immediately. The air inside them would compress to a fraction of its normal volume, and the lung tissue would fold and tear as the water forced its way in. Your sinuses would collapse, your eardrums would rupture long before you reached even a fraction of this depth. The tiny air pockets inside your bones, your inner ear, your intestines, all of it would be compressed beyond recognition. But the most unsettling part is what happens to your skeleton. At extreme ocean depths, scientists have confirmed that the water chemistry changes. Calcium, the mineral that gives your bones their hardness, dissolves more easily under extreme pressure and cold. Your bones would literally start to break down. Not in years, not in months. The process begins almost immediately. This is why some marine biologists long believed that no vertebrate, no animal with a backbone, could survive at the deepest points of the ocean. The chemistry should not allow it. Calcium should not hold together at those pressures. Any creature with a skeleton should, in theory, fall apart. And for years, that theory held. Until scientists started finding fish, living, moving fish at depths exceeding 26,000 feet. Fish with soft, translucent bodies that seem to break every rule about what bones can handle. Fish that had evolved to survive. Conditions that would dissolve a human skeleton in days. How they do it remains one of the great puzzles of deep-sea biology. Their bones are thinner and more flexible than any fish living near the top. Their cells contain special molecules that help proteins fold correctly, even under extreme pressure. Their bodies have almost no air-filled spaces. They have, over millions of years, redesigned themselves from the inside out. The trench does not care about the rules we wrote in textbooks. Life rewrote them. And the sounds it makes while doing so are unlike anything recorded on Earth. You might think that the deepest place on Earth would be silent. Miles of water above you. No wind, no waves, no engines, just stillness, emptiness, quiet. Scientists thought the same thing. Then they lowered a microphone to the bottom. In 2015, a team from the National Oceanic and Atmospheric Administration and Oregon State University dropped a specialized recording device called a hydrophone to the floor of Challenger Deep. The hydrophone was wrapped in a titanium case to survive the pressure and programmed to record continuously for 23 days. When they brought it back up and played the audio, they were stunned. The bottom of the Mariana Trench is loud. Not loud like a city street or a concert. Loud in a way that is difficult to describe. The recording captured a constant background hum, a deep, vibrating ambient noise that never stopped. Layered on top of that hum were specific sounds. Distinct, identifiable, and sometimes haunting. The most prominent sound was earthquakes. The Mariana Trench sits along one of the most active tectonic boundaries on Earth. The Pacific Plate is constantly grinding beneath the Mariana Plate, and every shift, every crack, every slip sends vibrations through the water. The hydrophone picked up quakes both near and far. Some were deep rumbles that lasted for minutes. Others were sharp jolts. Researchers also heard whale calls. Baleen whales, some of the largest animals on the planet, produce low-frequency sounds that can travel for thousands of miles through the ocean. Their moans and pulses, generated near the top of the water, traveled all the way down to the bottom of the trench. 7 miles of water could not stop them. The sounds were faint but unmistakable. During one stretch of the recording, a Category 4 typhoon passed directly overhead. The hydrophone captured the storm from below. The crashing of waves, the wind driving the ocean into chaos, all of it translated into deep, powerful vibrations that reached the bottom. A storm raging 7 miles above was audible on the ocean floor. There were also sounds that the team could not immediately identify. Strange pulses, low moans with no clear source. Some lasted just a few seconds. Others repeated at regular intervals. The researchers eventually attributed most of them to ship propellers, distant volcanic activity, and biological sources they could not pinpoint. One of the lead scientists on the project described the recordings as eerie. He said the team expected silence and instead found a complex soundscape, a world full of noise that had been playing for millions of years with no one to hear it. Sound behaves differently in the deep ocean. Water is denser than air, and sound waves travel through it about 4 times faster. At the extreme pressures of the trench, sound moves even faster and carries further. A noise made on one side of the Pacific can travel across the entire ocean basin without losing much energy. This means the trench is not isolated. It is acoustically connected to the entire ocean. Sounds from earthquakes in Japan, whale songs from the Southern Ocean, storms near the Philippines, They all arrive at Challenger Deep as a constant, overlapping stream of noise. The recording project also revealed something unexpected about the human impact on deep ocean sound. Ship traffic has increased dramatically over the past century, and the low-frequency noise from cargo ships and tankers now reaches even the most remote parts of the ocean. The hydrophone picked up propeller noise from vessels thousands of miles away. That means we are not just polluting the trench with plastic, we are polluting it with sound, and scientists do not yet fully understand what that means for the creatures living there. Because sound is not just background noise in the deep ocean, for many creatures, it is everything. It is how they find food, avoid predators, and communicate in a world without light. Flooding their environment with artificial noise could be disrupting survival behaviors millions of years old. The trench has a voice. We just were not listening. And in the darkness where sound is the only sense that works, something far stranger is happening with light. Sunlight is the engine that powers almost every ecosystem on Earth. Plants use it to grow. Animals eat the plants. Predators eat the animals. The chain begins with the sun. Remove it, and everything should collapse. In the ocean, that collapse starts faster than most people realize. When sunlight hits the water, it does not penetrate very far. The first thing to go is red light. Within about 30 feet, red wavelengths are absorbed by the water. This is why everything looks blue-green when you dive even a short distance down. The warm colors vanish almost immediately. By 200 feet, most of the visible light spectrum is gone. Orange, yellow, and green have been swallowed. Only faint blue remains, and it is fading fast. At 660 feet, scientists draw an official line. This is the bottom of what they call the photic zone, the layer of ocean where enough sunlight reaches to support photosynthesis. Below this depth, no plant and no algae can grow. The food chain that depends on sunlight effectively ends here, but the ocean keeps going. Below the photic zone, you enter what is called the twilight zone. It stretches from roughly 660 feet down to about 3,300 feet. Some faint light from above still exists here, but it is so dim that it is useless for photosynthesis. Your eyes might detect a faint blue glow if you looked upward. Looking down, there is nothing. And then, below 3,300 feet, even that last trace of sunlight is gone. Forever. You have entered the midnight zone, a world of permanent, absolute darkness. From this point all the way to the bottom of the Mariana Trench, no photon from the sun will ever reach you. Think about what that means. Everything below this line exists in a darkness more complete than any you have ever experienced on land. There is no night sky, no moonlight, no distant glow from a city. It is the total absence of light. And yet, the deep ocean is not truly dark. This is one of the most stunning discoveries in marine biology. In the midnight zone and beyond, a huge number of creatures produce their own light through a process called bioluminescence. Chemical reactions inside their bodies generate photons, creating flashes, pulses, and steady glows in a rainbow of colors. Scientists estimate that up to 90% of all animals living in the deep ocean are bioluminescent. The darkness is not empty. It is full of living lanterns. Some creatures use light to hunt. The anglerfish dangles a glowing lure from its head to attract prey into striking range. Some jellyfish pulse with blue light when disturbed, creating a flash that startles predators and gives them a chance to escape. Certain squid release clouds of glowing ink instead of dark ink, confusing anything chasing them. Others use light to communicate. Patterns of flashing and dimming act like a language in the dark, allowing animals to find mates, warn rivals, and coordinate group behavior. Some species flash in specific rhythms that are unique to their kind, like a biological identification, code, and some use light as camouflage. In the twilight zone, where faint sunlight still filters down, certain fish produce a soft glow on their bellies that matches the light from above. This eliminates their silhouette, making them invisible to predators watching from below. It is called counter-illumination, and it is one of the most elegant survival strategies in nature. The deeper you go, the stranger the light displays become. In the Hadal Zone, the deepest part of the ocean where the Mariana Trench sits, bioluminescence is rarer but still present. Some organisms glow faintly near hydrothermal vents. Others flash in response to disturbance, creating brief sparks in a world that has not seen sunlight in hundreds of millions of years. Every flash of light in the deep ocean is a small act of defiance against the darkness. And in the twilight zone, where the last traces of light fade out, there are hunters that have turned dimness itself into a weapon. Between 660 feet and 3,300 feet below the waves, the ocean enters a strange middle ground. Enough light filters down from above to create a faint, blue-grey glow, but not enough to see clearly. Shapes become shadows, movement becomes flickers, everything is half visible, half hidden. This is the Twilight Zone, and it is one of the most dangerous places in the ocean. The animals that live here have evolved for ambush, deception, and stealth. In a world of dim light, being visible means being eaten. So nearly every creature in the Twilight Zone has developed some way to disappear. Many fish in this zone are dark-colored. Black, deep red, or dark brown, colors that absorb what little light exists and make them nearly invisible. Some species have ultra-black skin that traps over 99% of all light that hits it. Scientists studying these fish found that their skin uses a special arrangement of pigment particles that prevents light from bouncing back. They are among the darkest living things on Earth. Others take the opposite approach. Instead of hiding in darkness, they hide in light. Hatchetfish, small silvery creatures with flat, blade-shaped bodies, line their bellies with rows of bioluminescent organs called photophores. These organs produce a faint downward glow that precisely matches the ambient light coming from above. To any predator looking up from below, the hatchetfish becomes invisible against the backdrop of the dim sky. Its silhouette vanishes completely. This technique is so effective that multiple unrelated species have evolved it independently. Lanternfish, bristlemouth fish, and certain squid all use counter-illumination. It is one of the most widespread survival strategies in the deep ocean. But the hunters here are just as clever. The Twilight Zone is home to some of the ocean's most efficient predators. Swordfish dive into this zone from above, plunging hundreds of feet to chase prey. Their eyes, especially, adapted with warming organs that keep their vision sharp in cold water, giving them an edge over prey whose eyes are sluggish in the chill. Sperm whales also hunt here, diving to remarkable depths to feed on squid. They navigate the darkness using echolocation, sending out powerful clicks that bounce off prey and return as echoes. A single sperm whale can dive over 3,000 feet and hold its breath for more than an hour while hunting. The Twilight Zone also hides one of the largest animal migrations on Earth. Every day, as the sun sets, billions of creatures rise from the deep toward the upper ocean to feed under the cover of darkness. When the sun rises again, they descend back into the Twilight Zone to hide. This is called the Deal vertical migration, and it involves more biomass than any other animal movement on the planet. Lanternfish alone are estimated to make up over half of all deep-sea fish biomass. Every night, uncountable numbers of them swim upward hundreds of feet to eat plankton near the waves, then sink back into the depths before dawn. If you could watch this happening across the entire ocean at once, it would look like the deep sea itself was breathing. This migration matters far beyond the Twilight Zone. As these creatures move up and down, they carry carbon with them. They eat carbon-rich food near the top and release waste and dead material at depth. Scientists believe this biological pump moves millions of tons of carbon from the upper ocean to the deep every year, making the Twilight Zone a critical player in Earth's climate system. Disturbing this migration through pollution, noise, or overfishing could have consequences that reach far beyond the ocean. But the twilight zone is only the entrance. Below it, the midnight zone begins in earnest. And in that permanent blackness, the rules of biology start to bend in ways that seem impossible. Animals grow to sizes they have no business reaching, and no one fully understands why. In the deep ocean, something strange happens to the size of animals. Creatures that are small near the top of the water grow much larger in the abyss. Scientists call it deep sea gigantism, and after decades of study, they still do not have a complete explanation for it. The pattern shows up across wildly different species. Isopods are a good example. Near coastlines and in shallow water, these crustaceans are tiny, usually less than an inch long. They look like small, armored pillbugs. You have probably seen their land relatives under rocks in your yard. In the deep ocean, isopods become monsters. Giant isopods can grow to over 20 inches long. They look like something from a science fiction movie. Hard, plated armor, large reflective eyes, powerful legs for crawling across the seafloor. Some species weigh over 3.5 pounds. How does a creature related to a backyard bug end up the size of a football in the deep ocean? Amphipods show the same pattern, near the waves. Most amphipods are small, shrimp-like creatures less than an inch long. In the Mariana Trench, scientists have found supergiant amphipods over 13 inches in length. Their exoskeletons are reinforced with calcium and, in at least one species found near the trench, aluminum. That is right. A shrimp relative that builds its armor partly out of metal. Giant squid are perhaps the most famous example. These animals can reach over 40 feet in length, with eyes the size of dinner plates. They live between 1,000 and 3,000 feet deep, and for centuries they were dismissed as sailor myths. It was not until 2004 that a living giant squid was photographed in its natural habitat. Japanese spider crabs, which live at depths of around 500 to 1,000 feet, can have a leg span of over 12 feet. Oarfish, which occasionally drift up from the deep, can exceed 36 feet long. In almost every case, the deep ocean version of a creature is dramatically larger than its shallow water cousin. Several theories try to explain this. The cold temperature theory suggests that cold water allows animals to grow larger because their cells can absorb more oxygen. Cold water holds more dissolved oxygen than warm water. And at depth, the extreme cold may allow animals to sustain larger bodies. This is confirmed to play a role, but it does not explain the full picture. The food scarcity theory argues the opposite angle. In the deep ocean, food is extremely rare. Meals arrive unpredictably as marine snow drifts down from above. A larger body can store more energy, allowing an animal to survive longer between feedings. Being big might mean being able to go weeks or months without eating. The predator theory points out that in the deep ocean, there are fewer predators. Large size is costly to maintain, and in shallow waters filled with hunters, being big makes you a target. In the deep, with fewer threats, there is less pressure to stay small. Evolution may allow gigantism simply because nothing is stopping it. The pressure theory is the most debated. Some researchers suggest that extreme pressure may influence cell growth and development in ways not yet fully understood. Studies have shown that certain deep-sea organisms have unique proteins and cell structures that could allow for unusual growth patterns. The honest answer is that scientists believe it is probably a combination of all these factors, and possibly others not yet identified. Deep-sea gigantism remains one of the open questions in marine biology. What makes it even stranger is how selective it is. Not every deep-sea creature is oversized. Some remain tiny. The pattern does not apply evenly. It seems to favor certain body plans, certain evolutionary lineages, and certain environments. The trench is home to giants and miniatures living side by side, and we do not fully know what decides which path a species takes. But one creature found near the trench took the concept of strange body design further than anyone imagined. It has a head made of see-through flesh and eyes that point straight up through its own skull. In 1939, a strange specimen was pulled from about 2,500 feet below the ocean near the Pacific coast. The creature was small, only about 6 inches long, with a soft body and large, green, tubular eyes. But the most unsettling detail was its head. It was completely transparent. You could see straight through it. The top of the fish's head was a clear, fluid-filled dome, like a living helmet made of see-through flesh. And through that dome, you could see its brain, its eyes, and the internal structures of its skull. Nothing was hidden. Everything was visible. Scientists named it the barrel-eye fish, though many call it the spookfish. And for nearly 70 years after its discovery, nobody fully understood how its eyes worked. Here was the problem. The barrel-eye's 2 large, barrel-shaped eyes were clearly visible through the transparent dome. They pointed straight up toward the faint light filtering down from above. This made sense. In the twilight zone, looking upward lets you spot the silhouettes of prey above you. But the fish also has 2 dark spots on the front of its face that look like eyes. For decades, scientists assumed those were the actual eyes, and that the green structures inside the head served some other purpose. The anatomy was confusing, and since barrelies are fragile creatures that live in deep water, they were almost impossible to study alive. It was not until 2009 that researchers at the Monterey Bay Aquarium Research Institute captured the first footage of a living barreley in its natural habitat using a remotely operated vehicle. What they saw changed everything. The green tubular structures inside the transparent dome were the eyes, and they could rotate. The fish was not locked into staring upward. It could pivot its eyes forward to look ahead, then tilt them back to scan the water above. The transparent dome gave the eyes a full range of motion inside a protected fluid-filled space. The dark spots on the front of the face were not eyes at all. They were olfactory organs, essentially a nose. This design is extraordinary. The barrel-eye floats almost motionless in the deep water, looking upward through its see-through head, scanning for the faint shadows of jellyfish and small creatures above it. When it spots food, it rotates its eyes forward, tilts its body upward, and swims directly toward the target. The transparent dome protects its eyes from the stinging tentacles of jellyfish, which are a major part of its diet. No other known fish has this combination of features. The transparent head, the rotating barrel eyes, the ability to look in multiple directions through its own skull. It is a design that seems engineered for a single purpose: hunting in near total darkness by watching for shadows above. And yet, for all its strangeness, scientists still know almost nothing about its daily life. How does it reproduce? How long does it live? How does it avoid predators? These questions remain unanswered. The barrel-eye lives too deep and is too delicate to study in captivity. Most specimens pulled to the top die quickly because the pressure change damages their tissues. The barrel-eye is a reminder that the deep ocean does not follow the rules of the world above. Transparent skulls, rotating eyes, bodies built for a life we can barely observe. And this fish lives in relatively shallow, deep water, if such a phrase even makes sense. It inhabits the upper edge of the deep sea, thousands of feet below the barrel-eye in the true midnight zone. Another hunter uses a completely different strategy. Where the barrel-eye watches for shadows, this creature creates its own light and uses it as a trap. It dangles a glowing lure in total blackness, and whatever comes close enough to investigate does not swim away. The deep ocean's most infamous predator is waiting, and its method of hunting is as cruel as it is effective. In the midnight zone, where no sunlight reaches and the only light comes from living things, one predator has turned the darkness itself into a weapon. The anglerfish sits motionless in the black water, barely moving, barely breathing, conserving every bit of energy. Extending from the top of its head is a long, thin rod tip with a small glowing bulb. That bulb pulses with soft, blue-green light. the only beacon in a world of total darkness. The light comes from bioluminescent bacteria living inside the bulb. The fish provides the bacteria with nutrients and shelter. The bacteria, in return, produce light. It is a partnership that has lasted millions of years, and it is deadly. In the deep ocean, light is irresistible. Where everything is black, any glow draws attention. Small fish, shrimp, and other creatures are pulled toward the anglerfish's lure the same way a moth is drawn to a porch light. They approach carefully at first, then move closer, until they are within striking range. The anglerfish's mouth is enormous relative to its body. Its jaws can open wide enough to swallow prey nearly twice its own size. Rows of thin, needle-like teeth angle inward, making escape nearly impossible for anything that enters. The strike is fast. One moment, the prey is drifting toward the light. The next moment, it is gone. This is ambush predation at its purest. The anglerfish does not chase, it does not pursue, it waits. And in the deep ocean, where food is rare and energy is precious, patience is the most valuable trait a predator can have. More than 200 species of anglerfish have been identified, living at a wide range of depths, from around 3,000 feet down to well over 10,000 feet. They come in bizarre shapes and sizes. Some are round and bloated, others are flat. Some are covered in fleshy filaments that make them look like drifting debris. But the strangest detail about anglerfish has nothing to do with hunting. It has to do with reproduction. In many species of deep-sea anglerfish, the males are tiny, dramatically, almost absurdly smaller than the females. A female might grow to over a foot long. The male of the same species might be less than an inch. In some cases, the male is less than a tenth the size of the female. When a male finds a female, he bites into her body and never lets go. Over time, his body fuses with hers. His eyes dissolve, his internal organs break down, his circulatory system merges with hers. Eventually, he becomes nothing more than a small lump attached to her body, providing sperm whenever she needs to reproduce. A single female can carry multiple males fused to her at the same time. Scientists have found females with 6 or more males permanently attached, each one reduced to a parasitic growth. This strategy evolved because of the deep ocean's greatest challenge. Finding a mate in total darkness across miles of empty water is nearly impossible. When a male anglerfish finally encounters a female, letting go could mean never finding another one. So he holds on, permanently. The anglerfish is one of the deep ocean's most studied creatures, but it still holds mysteries. Scientists do not fully understand how the bioluminescent bacteria pass from one generation to the next, and the deep ocean likely contains anglerfish species that have never been seen. For all its fame, the anglerfish is only one of thousands of predators using light in the dark. Dragonfish have bioluminescent organs along their bodies and can produce red light, which most deep-sea creatures cannot see, giving them an invisible spotlight to hunt with. Viperfish have light-producing organs inside their mouths, tricking prey into swimming directly into their jaws. The Midnight Zone is a war fought entirely in the dark, with light as both weapon and lure. And somewhere in this, darkness, another creature has taken a completely different approach to survival. It looks adorable, it acts friendly, and it is one of the most efficient killers in the deep sea. Floating through the deep ocean near the Mariana Trench, there is a creature that looks like it belongs in a children's cartoon. It has a round, soft body, 2 large, floppy fins on the sides of its head that wave gently as it moves, big, wide eyes, a smooth, almost friendly face. Scientists nicknamed it the Dumbo octopus because those ear-like fins resemble the flying elephant from the Disney movie. And by deep-sea standards, it is genuinely cute. It is also a ruthless hunter. The Dumbo octopus does not chase its prey through the water. It does not set traps or use bioluminescent lures. It moves slowly, drifting above the seafloor on gentle pulses of its fins, looking calm and harmless. Then, it finds something to eat, a worm, a small crustacean, a snail, and it swallows the prey whole, alive, in one motion. Unlike most octopuses, which tear food apart with their beaks, the Dumbo octopus engulfs its prey entirely. It wraps its webbed arms around the victim and forces it into its mouth in a single gulp. No chewing, no dismembering. The prey goes incomplete and is digested internally. It is efficient, quick, and surprisingly violent for something that looks so gentle. The Dumbo octopus lives at extreme depths. Some species have been found below 13,000 feet, and researchers have observed them as deep as 23,000 feet. They are among the deepest living octopuses ever recorded. One specimen was observed during a 2014 expedition on the research vessel Nautilus, floating near the seafloor at a depth that stunned the team watching the live feed. At these depths, the Dumbo octopus faces the same pressures, cold, and darkness that define the entire deep ocean. But its body is remarkably well adapted. Unlike shallow water octopuses, it does not have an ink sac. Total darkness. Squirting ink is pointless because no predator could see it. Evolution removed the feature entirely. Its body is also softer and more gelatinous than its shallow water relatives. At extreme pressures, a rigid body would be a disadvantage. The Dumbo's soft tissues can flex and adjust to the crushing force of the water without breaking. It moves through the deep ocean like a living balloon, almost weightless, barely disturbing the water around it. Scientists know remarkably little about the Dumbo octopus's reproduction. No one has ever observed mating behavior in the wild. Females are believed to carry eggs internally and attach them to rocks or the seafloor, but the details are largely unknown. How long do they live? How far do they travel? How many offspring do they produce? These basic questions remain unanswered for most species, and there are many species. The Dumbo octopus is not a single animal. It is a group of at least 15 known species, and scientists suspect there are more that have not been described yet. The deep ocean is so vast and so poorly explored that new varieties are discovered with almost every expedition. One thing researchers have noticed is that Dumbo octopuses seem to be found wherever the deep ocean floor has enough food to sustain them. They are not picky eaters. Worms, crustaceans, bivalves, anything small enough to swallow is fair game. This flexibility makes them one of the more successful predators in an environment where specialization can be a death sentence. The Dumbo octopus is a favorite of deep-sea researchers, partly because of its appearance and partly because encountering one on a dive is always unexpected. They do not cluster in groups. They drift alone through the darkness, appearing suddenly in the lights of a submersible like a ghost, then vanishing back into the black. It is a reminder that the deep ocean can be beautiful and terrifying at the same time. But below the Dumbo's range, even deeper in the trench, another fish was discovered that should not exist at all. A translucent, fragile creature found at a depth where scientists believed no vertebrate could survive. Its discovery forced biologists to rethink the limits of life itself. In 2014, during an expedition to the Mariana Trench led by researchers from the University of Hawaii, a camera was lowered to a depth of about 26,200 feet. It was one of several instruments deployed as part of the Hadal Ecosystem Studies program, designed to explore the deepest environments on the planet. When the footage was reviewed, scientists saw something that stopped them cold. A small, white, translucent fish drifted slowly across the screen. It had broad, wing-like fins and a long, eel-like tail. Its body was so see-through that you could make out parts of its internal organs. It moved with a slow, gliding motion, barely stirring the water, like a ghost floating through the blackness. It was a snailfish, and it was the deepest living fish ever recorded. The discovery was shocking because of a long-standing scientific assumption. At extreme depths, the pressure is so intense that calcium, The mineral that forms bones and teeth becomes highly soluble. It dissolves. This led many biologists to believe that fish, which need calcium for their skeletons, simply could not survive below a certain depth. The theoretical limit was somewhere around 27,000 to 28,000 feet. The snailfish found in the Mariana Trench was living right at that boundary, at a depth where its own skeleton should technically be dissolving. How it manages this is partly understood. The Mariana snailfish does not have a hard, mineralized skeleton like fish near the top of the ocean. Its bones are extremely thin, soft, and flexible. They bend rather than resist pressure. Its body is gelatinous, almost like jelly, with very little rigid structure. It has essentially minimized the amount of calcium it needs to function. Its cells also contain high concentrations of a special molecule called trimethylamine oxide. This molecule helps stabilize proteins under extreme pressure. Without it, the proteins inside the fish's cells would unfold and stop working, killing the animal. The snailfish produces this molecule in quantities that increase with depth, a direct biological response to the crushing conditions. The fish's appearance is part of its survival strategy. That translucent, ghostly look is not a flaw, it is a feature. With almost no rigid skeleton and a body made mostly of water and soft tissue, the snailfish's body compresses evenly with the water around it. There are no air pockets, no hard structures that would crack or implode. The pressure pushes on it from all sides, and the fish simply absorbs it. Researchers on the expedition filmed the snailfish multiple times during their deployment. Each time, it appeared as the same ghostly shape, gliding just above the seafloor, occasionally pausing near bait that had been placed for the cameras. It moved with no apparent urgency, no panic, no stress. It looked entirely at home in conditions that would kill every other fish on Earth. Since that discovery, additional snailfish sightings have been recorded at similar depths. In 2022, a snailfish was filmed at over 27,000 feet in the Izu Ogasawara Trench near Japan. Each sighting pushes the known limits of fish survival further. But the question lingers. Is the snailfish the absolute limit? Or could there be fish living even deeper that we have not found yet? The theoretical boundary based on calcium chemistry suggests there should be a hard cutoff. Below a certain depth, bones cannot hold together. But the snailfish already operates at that edge, and biology has a long track record of breaking theoretical limits. What we do know is that below the snailfish's range, life does not disappear. It changes form. Invertebrates, creatures without backbones, dominate the deepest parts. Amphipods, worms, sea cucumbers, and single-celled organisms thrive where fish cannot go. Life does not stop at the bone dissolution boundary. It just shifts to bodies that do not need bones at all. The Mariana snailfish stands at the edge of a biological frontier. Below it lies a world we have barely begun to explore. And in that world, one creature may be the most mysterious of all. A pale, ghostly octopus that appeared on camera, stunned the internet, and then vanished without explanation. In February 2016, a remotely operated vehicle operated by the National Oceanic and Atmospheric Administration was exploring a seamount near the Mariana Trench at a depth of about 14,700 feet. The vehicle was gliding above a flat, rocky bottom when something appeared in the camera that no one expected. A small, ghostly white octopus sat motionless on the rock. It was unlike any octopus scientists had ever seen. Its body was pale, almost completely white, with a smooth, featureless texture. It had no visible pigmentation, no patterns, no color at all. Its eyes were small and dark against the white flesh. It looked like a creature made of wax. The footage was broadcast on a live stream that the agency runs during its deep sea explorations. Within hours, the video went viral. Millions of people watched the small, pale octopus sitting calmly on the ocean floor, and the internet collectively lost its mind. Scientists on the live feed were just as surprised. One researcher said on camera that they had never seen anything like it. The octopus did not match any known species. Its depth, its color, its body shape, everything about it was new. The team informally nicknamed it Casper, after the friendly ghost, because of its pale, spectral appearance. The name stuck immediately. What made Casper even more unusual was its lack of typical octopus features. Most deep-sea octopuses have some pigmentation, even in total darkness. Casper looked almost gelatinous, as though its body was barely holding together. Its fins were small and delicate. It barely moved during the time the camera observed it. Scientists identified it as likely belonging to a group called incerate octopods. But within that group, it matched no described species. It was something entirely new. And then it was gone. The remotely operated vehicle moved on. The dive ended. And despite return expeditions to the same area, no one has found Casper again. The octopus appeared once, was filmed for a few minutes, and disappeared into the deep ocean. This happens more often than people realize. The deep ocean is so vast and so poorly explored that a single sighting may be the only evidence a species ever leaves behind. Scientists estimate that millions of deep-sea species have never been seen by human eyes. Casper may represent an entire population of pale octopuses living across the deep Pacific, and we would have no way of knowing unless a camera happened to land beside one. Since the original sighting, researchers have reported similar pale octopuses at a few other deep-sea locations, but none have been captured or studied in detail. Without a physical specimen, scientists cannot perform genetic analysis to formally describe it as a new species. Casper remains in scientific limbo, known to exist, observed on video, but officially unnamed. There is one additional detail that makes the story stranger. In a later expedition, researchers observed what appeared to be a similar type of pale octopus, guarding a clutch of eggs on the seafloor near manganese nodules. Small metallic lumps that form naturally on the deep ocean floor. This raised immediate concerns because mining companies have expressed interest in harvesting these nodules for their mineral content. If pale octopuses depend on manganese nodules as nesting sites, deep-sea mining could destroy their breeding grounds before we even know what species they are. The ghost octopus represents everything we do not know about the deep ocean. A creature that appeared without warning, defied classification, and vanished. It could be common or rare, widespread or confined to a single ridge. We simply do not know. And this is just one animal, one chance sighting. The Mariana Trench stretches for over 1,500 miles, and most of it has never been seen by any camera, any robot, or any human eye. What else is down there, just out of reach? The creatures we have discussed so far live in the water column and on the seafloor. But deeper still, inside the trench itself, scientists discovered something in the bodies of the animals that should horrify every person listening. In the deepest parts of the Mariana Trench, crawling across the sediment in total darkness, there are creatures that look like insects from a nightmare. They have segmented bodies covered in hard plated armor, multiple legs that grip the seafloor, long antennae sweeping the water ahead of them, reflective eyes that catch the faintest trace of light. They are amphipods, and in the Mariana Trench, they grow to unnatural, almost disturbing sizes. In shallow water, amphipods are small. Most species are less than an inch long. They look like tiny shrimp, darting through seaweed and sand, scavenging whatever they can find. You would barely notice them on a beach. They are one of the most common animals in the ocean, found at every depth and in almost every marine habitat on Earth. But in the Hadal Zone, the deepest layer of the ocean where the Mariana Trench sits, amphipods break the rules. Scientists have pulled supergiant amphipods from the trench that measured over 13 inches long. That is over a foot of armored crustacean, crawling through water that would crush a submarine. Their size alone is unsettling. But what makes them even stranger is how they build their bodies. In 2019, a team of researchers studying amphipods from the Mariana Trench discovered something unexpected in their exoskeletons. Along with the calcium that most crustaceans use to harden their shells, these deep-sea amphipods were incorporating aluminum into their armor. They were reinforcing their bodies with metal. This was the first time scientists had documented aluminum being used as a structural material in a living animal's exoskeleton. The researchers believe the aluminum provides extra strength to resist the extreme pressure at depth. In a world where the water pushes on you with over 1,000 times the force you feel at sea level, having a stronger shell is not a luxury. It is survival. But armor is only useful if you can find enough food to maintain a body that size. And food in the Hadal Zone is desperately scarce. Amphipods in the trench are scavengers. They eat whatever falls from the water above. Dead fish, whale carcasses, bits of decaying organic matter that drift down as marine snow. When a large animal dies and sinks to the trench floor, amphipods swarm it. Thousands of them converge on the carcass and strip it clean in a matter of hours. Then they scatter and wait, sometimes for weeks or months, until the next meal arrives. To survive between feedings, their bodies have adapted to extreme starvation. Scientists studying trench amphipods found that they can slow their metabolism to almost nothing, entering a state of near-suspended animation until food appears. Their digestive systems are efficient beyond anything seen in shallow water species, extracting every possible calorie from whatever they consume. They also have another survival trick. Amphipods in the trench practice cannibalism. When food is scarce enough, they eat each other. Larger individuals prey on smaller ones without hesitation. It is a grim but effective strategy in an environment where waiting for food from above could mean starvation. Traps lowered by researchers to the trench floor have captured amphipods within minutes of hitting the bottom. The animals seem to detect the bait almost instantly, likely through chemical sensors in their antennae that can pick up the faintest trace of food in the water. Some traps have returned to the surface packed with hundreds of amphipods, all fighting over a single piece of bait. The speed at which they arrive suggests the trench floor is more populated than it looks. The darkness hides them, but they are there, waiting, sensing, ready to swarm anything that carries the scent of food. And recently scientists cut these creatures open and found something inside their bodies that had nothing to do with the ocean. Something that came from us. Every single one of them was contaminated. In 2019, a team of British scientists published a study that should have made headlines around the world. They had collected amphipods from 6 of the deepest ocean trenches on Earth, brought them back to their laboratory, and carefully opened their digestive systems under microscopes. What they found inside was plastic. Not in some of them, in most of them. Over 80% of all the amphipods they examined had plastic fibers and tiny fragments lodged in their guts. The deeper the trench, the worse it got. In the shallower trenches, the contamination was high, but not total. In the Mariana Trench, the deepest of them all, the number was 100%. Every single amphipod pulled from the trench had plastic inside its body. Every one. The fibers were tested and identified. Most of them matched the synthetic materials used in everyday clothing and textiles. Polyester, nylon, acrylic. The kind of fibers that shed from your clothes every single time you run a washing machine. Millions of these tiny threads drain from the machine into the water supply, flow through treatment plants that are not designed to catch particles that small, and eventually reach the ocean. From there, the fibers begin to sink. They attach to particles of marine snow, the constant rain of dead organic material drifting toward the ocean floor. They get caught in currents that funnel debris into trenches. They travel through the water column for weeks, sometimes months, spiraling slowly downward through miles of cold, dark ocean. And once they reach the bottom of a place like the Mariana Trench, there is nowhere else to go. The The scientists describe the deep ocean trenches as the final sink for plastic pollution. Not a temporary storage place, not a waypoint, a permanent destination. On the ocean's upper layers, waves and sunlight can break down plastic over time. Currents can disperse it. At the bottom of a trench, none of that happens. The plastic sits in cold, dark, still water, and it stays there forever. The amphipods eat it because they eat everything. They are scavengers. They cannot tell the difference between a flake of organic matter and a thread of polyester. Their bodies process what they can and store what they cannot. The plastic accumulates in their tissues, and amphipods are not the only animals affected. Subsequent studies found microplastic particles in the sediment of the Mariana Trench itself. The mud at the bottom of the deepest place on Earth contains measurable amounts of plastic debris. Researchers from China analyzed sediment cores from the trench floor and found microplastics in every sample, at concentrations higher than those found in some coastal areas. That means the most remote, most inaccessible environment on the planet is more contaminated with plastic than some beaches. This discovery raises questions that scientists are only beginning to answer. What happens when microplastics enter the deep sea food chain at its base level? Amphipods are eaten by fish and other predators. If the amphipods are full of plastic, every creature that feeds on them is also consuming plastic. The contamination does not stay at the bottom. It moves upward through the food web. There is also a serious chemical concern. Plastics absorb and concentrate toxic chemicals from the water around them. Heavy metals, pesticides, and industrial pollutants bind to plastic particles over time. When an amphipod swallows a piece of plastic coated in these chemicals, it is not just eating trash, it is eating poison. The trench was supposed to be pristine. It was supposed to be the one place on Earth completely untouched by human activity, a place too deep, too remote, and too extreme for our influence to ever reach. But we reached it anyway. Not with submarines, not with cameras, with garbage. And the person who made this reality impossible to ignore did so during the deepest solo dive in recorded history. In April of 2019, a retired United States Navy officer and private equity investor named Victor Vescovo climbed into a submersible the size of a small car and dropped toward the bottom of the Mariana Trench. His vessel was called the Limiting Factor, a titanium pressure hull designed to reach the deepest points in every ocean on Earth. His mission was part of a larger expedition called the Five Deeps. The goal was to dive to the lowest point in each of the world's 5 oceans. The Mariana Trench was the final and most extreme challenge. On his first dive, Vescovo descended to 35,853 feet. That was 52 feet deeper than the previous record set by Don Walsh and Jacques Picard in 1960. He had gone further down than any human being in history. He spent 4 hours on the bottom. During those 4 hours, Vescovo explored the floor of Challenger Deep using cameras, mechanical arms, and observation windows. He saw life. Translucent sea cucumbers drifting above the sediment, shrimp-like amphipods with long antennae, a pink snailfish gliding through the blackness, brightly colored rocky outcrops that his team believed were formed by microbial activity. He also saw something that did not belong there, a plastic bag, sitting on the floor of the deepest place on Earth, crumpled and faded, resting on the sediment nearly 7 miles below the waves. Beside it, what appeared to be candy wrappers, human trash, at the absolute bottom of the world. Vescovo later described the discovery as both incredible and sobering. He had traveled further down than any human in history and found evidence that we had already been there, not in person, in the form of our waste. The dive was not his only one. Vescovo returned to Challenger Deep multiple times during the expedition, making him the first person ever to dive to the bottom of the trench more than once. Across his dives, his team collected rock samples, biological specimens, and water samples for scientific analysis. They also discovered what they believed were at least 4 new species of crustacean. These were small, prawn-like creatures found at extreme depth. Animals that had likely never been seen before by any human or camera. Confirming them as new species would require laboratory analysis, but the initial observations were promising. One dive took Vescovo to the Serena Deep, another canyon within the Mariana Trench located about 128 miles northeast of Challenger Deep. The Serena Deep is the third deepest point in the ocean, plunging to over 35,400 feet. Vescovo and a colleague spent nearly 3 hours there and retrieved a piece of mantle rock from the trench wall, a sample from deep within the Earth's interior that had been pushed upward by the grinding of the tectonic plates. Across all of his Mariana Trench dives, Vescovo spent more time at the bottom than any human in history. He saw more of the trench floor with his own eyes than Piccard, Walsh, and Cameron combined. And his verdict was clear. The trench is not a dead zone. It is alive, inhabited, and geologically active. It is also polluted. The two realities exist side by side, 7 miles below the Pacific. The limiting factor itself was a technological leap. Unlike the Trieste, which could only go down and come back up, the limiting factor was fully maneuverable. It could drive across the seafloor, stop, turn, and hover. It was built to be reused, dive after dive, without needing major overhauls between missions. This mattered because it meant the deep ocean was no longer a place for one-time stunts. It was becoming accessible for repeated scientific exploration. But what Vescovo's dives confirmed about plastic raised a much darker question. If trash has already reached the deepest point on the planet, where exactly is it safe from us? The plastic bag at the bottom of Challenger Deep was not an isolated piece of litter that somehow drifted to the wrong place. It was a symptom of something much larger. Scientists now understand that the Mariana Trench, along with every other deep ocean trench on Earth, acts as a collection point for human waste, not by accident, by physics. Ocean trenches are shaped like funnels. Their long, narrow walls slope inward toward a flat bottom. Currents flowing across the ocean floor push debris along until it reaches the edge of a trench, and then a gravity takes over. Particles, sediment, and anything caught in the flow slides down the walls and settles at the lowest point. Once it reaches the bottom, there is no mechanism to push it back out. On land, plastic can be picked up, recycled, or at least moved somewhere else. In the upper ocean, waves and ultraviolet light slowly break it into smaller pieces. Currents disperse it across wide areas, but at the bottom of a trench, none of those forces exist. There is no sunlight to degrade the plastic, no wave action to scatter it, no current strong enough to carry it upward. The trench is a one-way trip. Researchers from multiple countries have confirmed this through sediment analysis. Core samples taken from the floor of the Mariana Trench contain microplastic, concentrations that are, in some cases, higher than what has been measured at the mouths of major rivers. The bottom of the deepest ocean is more polluted with tiny plastic particles than some of the most industrialized waterways on Earth. A study published by Chinese researchers analyzed sediment from multiple depths within the trench and found microplastics at every level they tested. The particles were not limited to the surface layer of sediment. They had been mixed into deeper layers, meaning plastic has been accumulating there for years, possibly decades. The trench is not just collecting new waste, it is building a layered record of contamination that grows thicker with every passing year. The types of plastic found are telling. Polyethylene terephthalate, the material used in plastic bottles. Polyester from clothing fibers. Cellophane from food packaging. Polystyrene from foam containers. The full catalogue of modern consumer products, shredded into particles smaller than a grain of rice, sitting 7 miles under the Pacific Ocean. And the problem is accelerating. Global plastic production has increased every year for decades. An estimated 150 million metric tons of plastic are currently circulating in the world's oceans. Every year, millions more enter the water. A portion of that inevitably sinks, and a portion of what sinks eventually reaches the trenches. Scientists studying this issue face a frustrating and almost helpless reality. Even if the world stopped producing plastic tomorrow, the material already in the ocean would continue sinking for years. The trenches would continue filling. The contamination that already exists at the bottom of the Mariana Trench is, for all practical purposes, permanent and irreversible. There is no cleanup technology that can operate at those depths. No robotic system capable of filtering microplastics from trench sediment 7 miles below the waves. The technology simply does not exist, and building it would be one of the greatest engineering challenges in history. The deep ocean was once thought to be the last place on Earth beyond human influence. A place so hostile, so remote, and so difficult to reach that it would remain untouched for centuries. That assumption was wrong. We polluted the deepest point on the planet without ever needing to visit it. Our trash found the way down on its own. But pollution is only one part of the trench's story. Beneath the sediment, beneath the plastic, beneath the still water, the Earth itself is alive. Cracks in the ocean floor release superheated water loaded with chemicals, and around those cracks, in temperatures that should sterilize everything, entire ecosystems flourish. Deep beneath the ocean floor near the Mariana Trench, the Earth's crust is cracked and unstable. Seawater seeps down through those cracks, sometimes miles into the rock, where it encounters magma chambers and superheated stone. The water heats up rapidly, absorbs minerals and chemicals from the surrounding rock, and then blasts back upward through openings in the seafloor called hydrothermal vents. What comes out is not ordinary water. The fluid pouring from these vents can exceed 700 degrees. That is hotter than the melting point of lead. It only remains liquid because the extreme pressure at the ocean floor prevents it from turning to steam. If that same water were brought up near the waves, it would flash into gas instantly. The fluid is also loaded with dissolved chemicals. Hydrogen sulfide, which is toxic to most life on Earth. Heavy metals like iron, copper, and zinc. Dissolved minerals that precipitate out of the water the instant they hit the cold surrounding ocean, forming tall, chimney-like structures around the vents. Some of these chimneys grow rapidly, adding inches of new mineral deposits in a single day. These chimneys come in two varieties, black smokers and white smokers. Black smokers produce the hottest fluid. As the superheated, mineral-rich water shoots upward and meets the freezing ocean, dark particles of metal sulfide crystallize instantly, creating a billowing plume that looks like thick, black smoke pouring from a factory chimney on the seafloor. The structures themselves can grow over 60 feet tall, building up layer by layer as minerals pile on top of each other over years and decades. White smokers are cooler. Their fluid temperatures typically sit below 570 degrees. They produce lighter colored minerals, mainly barium, calcium, and silicon, which create a pale, milky plume. White smokers are often found along the volcanic arc near the Mariana Trench, where the chemistry of the underlying rock produces more acidic fluids. In the back arc region west of the trench, scientists have found black smokers at extreme depths. One vent discovered during a 2015 expedition sits at over 13,900 feet, making it one of the deepest hydrothermal vents ever recorded on Earth. Only 3 other known vents go deeper. The area around a hydrothermal vent is a battlefield of extremes. Within inches, the water temperature can swing from near freezing to hundreds of degrees. The chemistry shifts from normal seawater to a toxic soup of dissolved metals and gases. Any organism living near a vent has to tolerate conditions that would kill virtually every other living thing on the planet. And yet, the areas around vents are among the most densely populated habitats in the deep ocean. Mats of bacteria coat the rocks near vent openings. These bacteria do not need sunlight. They use a process called chemosynthesis, converting hydrogen sulfide and other chemicals into energy the same way plants use sunlight for photosynthesis. They are the foundation of an entire food chain that exists independently of the sun. Shrimp cluster around vent chimneys in enormous, dense swarms, grazing on the bacterial mats that coat the rocks. Crabs pick their way across surfaces, crusted with mineral deposits, moving carefully through water that shifts from freezing to scalding within inches. Tube worms, with bright red plumes, extend from hard casings anchored to the seafloor, filtering nutrients from the vent water. These vent communities are isolated from each other and from the rest of the ocean. Each one is like an island, surrounded by miles of barren seafloor. The creatures living there cannot easily travel to the next vent. If a vent dies, which they do when the geological activity beneath them shifts, the community around it dies with it. But what scientists found at one particular volcano near the trench was unlike anything else on Earth. And the only known comparison exists hundreds of millions of miles away, on a moon orbiting Jupiter, on the flanks of an underwater volcano called Daikoku, roughly 1,345 feet below the ocean near the Mariana Islands. Scientists found something that should not exist on this planet: a pool of liquid sulfur, churning, bubbling, and glowing on the seafloor. The pool sits inside a shallow depression on the volcano's summit, like a cauldron carved into the rock. The sulfur inside it is molten, heated by volcanic activity beneath the seafloor to temperatures high enough to keep it in liquid form. From above, it appears black and oily, shifting and rippling as gases push up through it from below. This is confirmed science, documented during multiple expeditions by the National Oceanic and Atmospheric Administration. Researchers captured footage of the sulfur pool during their submarine Ring of Fire expeditions in 2004 and 2006. The video shows a dark, restless liquid surface surrounded by pale mineral deposits, venting gas in uneven bursts. There is only one other known location in the entire solar system where liquid sulfur has been found on a surface, and it is not on Earth, it is on Io, one of the 4 large moons of Jupiter. Io is the most volcanically active body in the solar system. Its surface is covered in erupting volcanoes that spew sulfur across the landscape, painting the moon in shades of yellow, red, and orange. Lakes of liquid sulfur sit in craters across its face. The pool on Daikoku is the only place on Earth that mirrors what happens on Io. A tiny pocket of alien geology sitting on the floor of the Pacific Ocean over 1,000 feet underwater, near the deepest trench on the planet. Scientists believe the sulfur pool forms because of the specific chemistry of the Daikoku volcano. Volcanic gases rich in sulfur dioxide rise through cracks in the rock and react with seawater, producing elemental sulfur that accumulates in the depression. The intense heat from the volcano keeps the sulfur above its melting point, maintaining the pool in its liquid state. If the volcanic activity ever slowed or stopped, the sulfur would cool, solidify, and the pool would freeze into a solid mass of yellow stone. The pool is not large. Estimates suggest it is only a few yards across, but its existence has major implications for our understanding of planetary geology. If Earth can produce features identical to what we see on Jupiter's moons, then the reverse might also be true. The chemical processes that create life-supporting environments on our planet's deep sea floor could be happening right now on worlds we have not yet explored. This is not a small idea. It is one of the central questions driving the search for life beyond Earth. Around the sulfur pool, life does exist, though in limited forms. Researchers have observed small flatfish resting on the rocks near the pool's edge. Microbial mats grow on the surrounding mineral surfaces. The environment is harsh, with toxic gases and extreme temperatures, but organisms have found ways to tolerate it. The Daikoku volcano is part of a larger chain of underwater volcanoes stretching north of Guam along the Mariana volcanic arc. Many of these volcanoes are hydrothermally active, producing vents, seeps, and chemical features that scientists are still cataloging. During the 2004 expedition alone, the team made several first-time discoveries, including the first direct observation of an erupting submarine volcano. These volcanoes are not ancient and dormant. They are active right now. They erupt. They vent. They reshape the seafloor around them in real time. And they produce some of the most extreme chemical environments found anywhere on our planet. Just a short distance from Daikoku, another volcano produces something equally strange. A stream of pure liquid carbon dioxide, bubbling up from the rock like an underwater champagne fountain. Scientists gave it a fitting name. And what lives around it raises even bigger questions about where life can survive. On the slopes of an underwater volcano called Northwest Eifuku, about 1,600 feet below the ocean near the Mariana Islands, something is bubbling out of the seafloor that looks like sparkling water. Streams of small, shiny droplets rise from cracks in the rock and float upward through the water column, catching the lights of passing submersibles. The droplets shimmer and twist as they ascend, looking almost festive like the bubbles in a glass of champagne. Scientists named it the champagne vent. But what is coming out of the rock is not air. It is not water vapor. It is liquid carbon dioxide, pure, pressurized, and released directly from the volcanic system below. This is one of only 2 known locations on Earth where liquid carbon dioxide vents from the seafloor. The extreme pressure at this depth keeps the carbon dioxide in liquid form instead of allowing it to expand into gas as it would near the waves. At normal atmospheric pressure, carbon dioxide is a gas. Down here, the ocean squeezes it into a dense liquid that behaves almost like oil, forming droplets that wobble and rise through the seawater. The vent fluid is also extremely hot. Temperatures around the champagne vent reach over 217 degrees. The water surrounding the vent openings is thick with white mineral deposits. Created as dissolved chemicals in the hot fluid, react with the cold ocean and crystallize instantly. These deposits form soft, crumbly structures that scientists call white smokers, and they coat the rocks around the vent in pale, ghostly layers. The gas and fluid escaping from the vent are also highly acidic. The pH near the openings drops significantly, creating a localized pocket of corrosive water that would dissolve the shells of most marine organisms. And yet, life thrives here. Mussels cluster around the vent openings, anchored to rocks just inches from where the acidic fluid pours out. Shrimp crawl across the mineral crusts. Bacterial mats coat every available surface, feeding on the chemicals in the vent fluid and forming the base of a food chain that operates entirely without sunlight. The mussels are especially interesting to scientists. They live in water that is more acidic and mineral-rich than almost any other habitat where mussels are found. Their shells are thinner than those of mussels in shallow water, likely because the acidic conditions make it harder to build and maintain calcium carbonate structures. But they survive. They reproduce. They form dense colonies. This matters because ocean acidification is one of the most serious threats facing marine life globally. As carbon dioxide from human activity dissolves into the ocean, the water becomes more acidic. Coral reefs, shellfish, and countless other organisms that depend on calcium carbonate structures are already being affected. Scientists studying the Champagne vent see it as a natural laboratory, a preview of what parts of the ocean could look like if acidification continues. The organisms living near the vent have adapted to conditions that may soon become common across much wider areas of the ocean. Understanding how they survive could help predict which species will endure as ocean chemistry changes and which ones will not. Northwest Eifuku is part of the same volcanic arc as Daikoku, the volcano with the sulfur pool. Together they represent some of the most chemically extreme environments on the planet. Liquid sulfur on one volcano, liquid carbon dioxide on another. Both located within the Mariana Trench Marine National Monument. Protected by law but barely explored by science, the Champagne vent and the sulfur pool share one critical feature. They both prove that life can establish itself in conditions once thought impossible. Toxic water, extreme acidity, temperatures that would sterilize a hospital. And they both point to a much larger idea. If life can survive in these conditions on Earth, the same chemistry might support life on worlds we have not reached yet. But before we look outward, there is one more discovery from the trench that changed what biologists thought was possible. An entire food chain, operating in total darkness, powered by nothing but chemistry. Almost every living thing on Earth depends on the sun. Plants capture sunlight and convert it into energy. Animals eat the plants. Predators eat the animals. Remove the sun, and the entire chain collapses. This has been the central rule of biology since we first understood how ecosystems work. The deep ocean broke that rule. Around hydrothermal vents and chemical seeps on the floor of the Mariana Trench, entire ecosystems thrive in total darkness, powered not by sunlight, but by chemical reactions happening inside the Earth itself. The process is called chemosynthesis, and it is one of the most important discoveries in the history of biology. Here is how it works. Hydrothermal vents release fluids loaded with chemicals like hydrogen sulfide, methane, and dissolved metals. Certain bacteria can use these chemicals the way plants use sunlight. They oxidize the chemicals, breaking them apart and capturing the energy released in the reaction. That energy is then used to build organic molecules, the same building blocks that photosynthetic organisms create using light. These bacteria form the base of a food chain that has nothing to do with the sun. Other microorganisms graze on the bacteria. Small invertebrates eat the microorganisms. Larger animals eat the invertebrates. The entire community exists in complete independence from the sunlit world above. This was first discovered in 1977 when scientists exploring the Galapagos Rift found thriving communities of giant tube worms, clams, and mussels clustered around hydrothermal vents over 8,000 feet deep. The discovery stunned the scientific community. Nobody expected to find large, complex life in a place with no access to sunlight. Since then, chemosynthetic communities have been found at hundreds of vent sites around the world, including multiple locations within the Mariana Trench system. Each one operates on the same principle. Chemical energy from the Earth replaces solar energy from the sky, and life builds itself around the difference. The implications of this are enormous, and they extend far beyond the ocean. If life can sustain itself entirely on chemical energy from geological processes, then sunlight is not a requirement for life. This single fact rewrites the equation scientists use when searching for habitable worlds in the solar system and beyond. Before chemosynthesis was understood, the search for extraterrestrial life focused almost entirely on finding planets in the habitable zone, the narrow band of distance from a star where liquid water can exist on the surface and sunlight can power photosynthesis. Worlds outside that zone were considered dead by default. Chemosynthesis blew that assumption apart. A world does not need to be close to a star to support life. It does not need warmth from above or light from any direction. It just needs liquid water, rock, and enough internal heat to drive chemical reactions. Those conditions exist on several bodies in our own solar system that were previously dismissed as lifeless. Jupiter's moon, Europa, has a global ocean of liquid water beneath a thick shell of ice. Saturn's moon, Enceladus, shoots plumes of water vapor into space from cracks in its surface, and those plumes contain hydrogen, a potential fuel for chemosynthetic life. Both moons have the rocky cores that could provide the chemical ingredients. The vents at the bottom of the Mariana Trench are the closest thing we have to a working model of what life on those worlds might look like. Darkness, extreme pressure, no sunlight, chemical energy driving a food chain from the ground up. Every discovery made in the trench adds a data point to that model. Every new species found at a vent tells scientists something about what is biologically possible in the absence of light. The trench is not just the deepest place on Earth. It may be a preview of life on other worlds. And the most recent expedition to the trench, conducted by a Chinese submersible in 2024, found the largest and deepest community of creatures ever documented in these conditions. In 2024, the Chinese research submersible Striver descended into the Mariana Trench 23 times. The vehicle, built to withstand the full pressure of the Hadal Zone, carried scientists to depths ranging from 8,200 feet to over 31,000 feet. Each dive lasted hours. Each one brought back footage and samples that no human had ever collected. What they found on those dives rewrote what scientists believed about life at the bottom of the ocean. Fields of tube worms. Not a few scattered individuals. Fields. Dense clusters of worms growing up to 12 inches long, their bodies anchored to the seafloor, their feathery plumes extended into the water to filter nutrients. Surrounding them, piles of clams and mussels packed into the sediment so tightly that the bottom looked like a crowded city rather than a barren wasteland. The footage was published in the journal Nature in 2025. The study's authors called it the discovery of the deepest and most extensive chemosynthesis-based communities known to exist on Earth. Previous expeditions had found single-celled organisms and small invertebrates at extreme depths. Microbial mats had been documented. A few scattered tube worms had been observed at vent sites around the world. But nobody had found anything like this. A thriving, densely populated ecosystem of large animals nearly 6 miles below the waves. The organisms were clustered around cold seeps, areas where methane and other chemicals ooze slowly through cracks in the seafloor. Unlike hydrothermal vents, which blast superheated fluid, cold seeps release their chemicals at temperatures close to the surrounding water. The flow is gentle, the chemistry is different, but the principle is the same. Bacteria at the base of the food chain convert chemicals into energy, and larger organisms build their lives around them. The tube worms found by the Striver team are particularly significant. Tube worms are well known from shallower vent sites, where they can grow over 6 feet long, but finding them at Hadal depths, in conditions where the pressure exceeds 1,000 atmospheres, was not expected. Their bodies must withstand forces that would crush most biological structures. The clams and mussels found alongside the tube worms were also remarkable. Their shells appeared thinner and more fragile than those of shallow water relatives, likely an adaptation to the extreme pressure and the chemistry of the water. Scientists believe the shells are thinner because building and maintaining heavy calcium structures at these depths requires enormous energy. The researchers also found what they described as compelling evidence that the methane fueling the ecosystem was being produced by microbes in the sediment below. This means the entire food chain, from bacteria to tube worms to clams, was powered by biological methane production deep in the Earth's crust. Life feeding on the chemical output of other life in total darkness under crushing pressure. The discovery has a wider implication that the research team was careful to highlight. The Mariana Trench is not the only deep ocean trench on Earth. There are over 24 major Hadal trenches scattered across the world's oceans. If chemosynthetic communities this extensive exist in the Mariana Trench, similar ecosystems could exist in every one of them. The deep ocean floor may be far more inhabited than anyone previously imagined, and most of those trenches have never been explored at all. The Striver's 23 dives covered only a tiny fraction of the Mariana Trench's total area. The trench stretches for over 1,500 miles. The submersible explored a few specific sites. Between those sites, vast stretches of seafloor remain completely unseen. What is living in those gaps? What other colonies are flourishing in the dark, powered by chemistry alone, waiting to be found? The trench keeps answering questions and then immediately raising bigger ones. And one of the strangest features near the trench is not alive at all. It is a geological structure so massive that scientists struggle to believe their own measurements. The discovery of thousands of large animals living at Hadal depths inside the Mariana Trench did more than add a new entry to the catalogue of deep sea life. It challenged a core assumption that had shaped deep ocean biology for decades. For years, the scientific consensus held that the Hadal Zone was too extreme for large, complex organisms. The pressures were too high. The food supply was too scarce, the cold was too constant. Individual creatures might survive there. Bacteria could endure almost anything. But dense, thriving communities of large invertebrates? That was not supposed to happen. The reasoning was straightforward. Large animals need a lot of energy. Energy in the deep ocean comes from two sources: marine snow drifting down from above, which is sparse and unpredictable, and chemosynthesis at vents and seeps, which was thought to be limited to isolated pockets. Neither source seemed sufficient to support a large, permanent population at Hadal depths. The Striver's discovery proved that reasoning wrong. The tube worm and clam colonies were not clinging to survival in a barren wasteland. They were flourishing. Dense aggregations covering significant areas of the seafloor. Organisms that had clearly been living and reproducing at these depths for generations. This was not a temporary outpost. It was a permanent ecosystem. The key factor that biologists had underestimated was the scale of chemical seepage. The cold seeps feeding these communities were not tiny, isolated cracks. They were extensive networks of fissures releasing methane across wide areas of the trench floor. The methane was being produced by microbial activity in the sediment, meaning the fuel source was essentially self-renewing. As long as the geology remained active and the microbes kept producing methane, the food chain would keep running. This changes the math entirely. Scientists had calculated the energy budget of the Hadal zone based on the assumption that most food had to fall from above. With chemosynthesis operating at this scale, the energy available to deep-sea communities is far greater than previous models predicted. The implications extend to how we think about other trenches. The Mariana Trench is the most famous, but it is not unique in its geology. Subduction zones around the Pacific are creating similar conditions in the Tonga Trench, the Kermadec Trench, the Philippine Trench, and others. If chemical seeps at Hadal depths can support this level of life in the Mariana Trench, there is no reason they could not do the same elsewhere. Marine biologists now face a deeply humbling realization. The models used to estimate life in the deep ocean were based on incomplete data. The discoveries from the Striver suggest that the deep sea may host far more biomass, far more diversity, and far more complexity than anyone predicted. And we have explored almost none of it. The Hadal zone covers a surprisingly large area. Trenches deeper than 20,000 feet exist in every major ocean basin. Combined, they represent hundreds of thousands of square miles of seafloor. Less than 1% of that area has been observed by cameras, robots, or human eyes. What the Striver found in its 23 dives was a glimpse through a keyhole. The room behind the door could contain entire ecosystems, species, and biological processes that no one has documented. The pace of discovery supports this conclusion clearly. Every major expedition to a deep ocean trench in the last decade has returned, with new species, new ecological data, and new questions. The pattern is consistent. We go down, we find something we did not expect, and we realize how much we are missing. The trench keeps humbling us. But the living systems are only part of the story. The geology of the Mariana Trench region contains some of the most extreme features on the planet, and one of them is a mud volcano so large that its dimensions challenge what geologists thought was possible. Near the Mariana Trench, rising from the deep ocean floor, there are mountains that do not erupt lava. They erupt mud. These are mud volcanoes, and the ones found in the Mariana region are the largest known on Earth. The biggest of them stretches 31 miles across and rises over a mile above the surrounding seafloor. That is a single geological structure wider than some entire island nations. Built not from molten rock, but from sediment, water, and gas, squeezed up from deep inside the Earth. Mud volcanoes form in subduction zones where one tectonic plate is diving beneath another. As the Pacific Plate descends beneath the Mariana Plate, immense pressure squeezes water and sediment out of the sinking rock. That material has to go somewhere. It pushes upward through fractures in the overlying plate and erupts at the seafloor, building massive mounds of mud, clay, and fragments of deep rock called serpentinite. The process is slow compared to a traditional volcanic eruption. There are no explosions, no rivers of lava, no ash clouds. The mud oozes upward gradually, spreading outward as it accumulates. Layer after layer builds on itself over time. Over millions of years, these oozing eruptions have built structures of staggering size that dwarf most features found on the ocean floor. The fluids released by mud volcanoes are chemically unusual. They are rich in hydrogen, methane, and other gases produced by reactions between seawater and the minerals in the sinking plate. In some locations, the hydrogen output is significant enough to attract scientific interest as a potential future energy source. The Mariana mud volcanoes represent the only place on Earth where active mud volcanoes of this size release hydrogen at measurable rates. No other region even comes close. These fluids also support life. Near the bases of several mud volcanoes, scientists have found thriving communities of clams, corals, sea anemones, and crabs clustered around seep sites where chemicals reach the seafloor. One such site, called the Shinkai Seep Field, was discovered just north of Challenger Deep and represents one of the deepest known chemosynthetic communities associated with a mud volcano. The serpentinite rock, pushed up by mud volcanoes, is itself a subject of intense scientific interest. Serpentinite forms when minerals in the ocean crust react with water under extreme pressure and heat. The chemical reaction, called serpentinization, releases significant amounts of heat and hydrogen. Some researchers believe this same process could be happening right now on other planets and moons with rocky interiors and liquid water, potentially creating habitable conditions deep below frozen surfaces without any need for sunlight or volcanic magma. The mud volcanoes near the Mariana Trench are also windows into the Earth's hidden interior. The material they push to the seafloor comes from depths that are otherwise completely inaccessible to science. By studying mud volcano samples, geologists can learn about conditions tens of miles below the ocean floor, deep inside the subduction zone itself. It is like having a natural drill that brings material from the deep Earth to a place where scientists can collect and analyze it without ever digging down. Despite their size and scientific importance, the Mariana mud volcanoes remain almost entirely unexplored. Most have been mapped only by sonar. Only a handful have been visited by remotely operated vehicles. The surfaces of these massive structures, their slopes, their craters, their seep communities, are largely unknown. Scientists estimate there are at least 18 major mud volcanoes and thermal vent sites within the boundaries of the Mariana Trench Marine National Monument. Each one represents a unique chemical environment with the potential to host undiscovered species and previously unknown geological features that could reshape our understanding of deep Earth processes. Beneath these mud volcanoes, the rock that makes up the ocean floor tells its own story. And in the case of the Mariana Trench, that story stretches back further than almost anything else on the seafloor. The rock at the bottom of the Mariana Trench is ancient. Not old in the way mountains or canyons are old. Old in a way that connects the present moment to a time before most life on Earth existed in its current form. The oceanic crust along the western edge of the Pacific Plate, the rock that is diving beneath the Mariana Plate, and creating the trench, is approximately 170 million years old. That dates it to the Jurassic period. When this rock first formed at a mid-ocean ridge somewhere in the Pacific, dinosaurs roamed every continent. The Atlantic Ocean did not exist. The world was unrecognizable. Since then, this slab of crust has been traveling slowly westward across the Pacific floor, pushed by the same spreading forces that created it. Inch by inch, year by year, for 170 million years, it has been on a journey that ends at the Mariana Trench, where it finally bends downward and plunges back into the Earth's interior. This makes it some of the oldest oceanic crust anywhere on the planet. Most oceanic crust is much younger because it is constantly being recycled. New crust forms at mid-ocean ridges, spreads outward, and eventually sinks at subduction zones. The average age of the ocean floor is only about 80 million years. The rock entering the Mariana Trench is over twice that age. Its age matters for several reasons. First, older crust is colder and denser than younger crust. After 170 million years of cooling, this rock has become extremely heavy compared to the warmer, younger Mariana plate riding above it. That density difference is a major reason the trench is so deep. The heavy old plate sinks more steeply and pulls the ocean floor down further, creating the extreme depths of Challenger Deep. Second, the age of the crust tells scientists about the forces driving plate tectonics. The Mariana subduction zone is one of the fastest and steepest on Earth. The Pacific plate descends at a sharp angle, which contributes to the trench's narrow, deep profile. Understanding why this particular subduction zone behaves the way it does helps geologists predict how other plate boundaries around the world might evolve over millions of years. The data gathered here shapes computer models used to study subduction zones in Japan, South America, and the Mediterranean. Third, the rock carries a chemical record. Over millions of years, the crust has absorbed water, minerals, and even biological material from the ocean above. As it sinks into the mantle, all of that absorbed material goes with it. Some of it is released at depth, contributing to the chemistry of volcanic eruptions in the island arc above. Some of it may be carried deep into the earth, potentially influencing the composition and behavior of the mantle on geological timescales that stretch beyond human comprehension. In 2019, Victor Vescovo's team retrieved a sample of mantle rock from the inner wall of the Mariana Trench. This rock had been pushed upward from deep within the subduction zone by the grinding of the two plates. Analyzing it gave scientists a direct window into material from tens of miles below the ocean floor. Material that had not been exposed for millions of years. The Mariana Trench is not just a hole in the ocean, it is a geological conveyor belt, pulling the Earth's oldest seafloor rock back into the interior of the planet. It is destruction and recycling happening simultaneously, on a timescale so vast that it makes all of human history seem like a single breath. Civilizations have risen and fallen, ice ages have come and gone, and through all of it, this slab of ancient rock has been inching toward its final descent. And this process does not happen quietly. The collision of these two enormous plates generates forces that can be felt across an entire ocean, thousands of miles from the trench itself. The Mariana Trench is one of the most seismically active places on the planet. The Pacific plate grinding beneath the Mariana plate does not slide smoothly. It catches, sticks, builds pressure, and then releases it in sudden, violent jolts. These are earthquakes, and along the Mariana subduction zone, they happen constantly. Most of them are small, tiny tremors that register on sensitive instruments, but are never felt by anyone. The seafloor shudders, the water vibrates for a moment, and everything settles. Thousands of these micro-earthquakes occur every year along the trench, but some of them are not small. Subduction zones are responsible for the most powerful earthquakes on Earth. The 2011 earthquake off the coast of Japan, which triggered a devastating tsunami and the Fukushima nuclear disaster, occurred at a subduction zone. The 2004 Indian Ocean earthquake, which killed over 200,000 people, also originated at a subduction zone. These are among the most destructive natural events in recorded history. The Mariana Trench's subduction zone is capable of producing similar earthquakes. The geology is the same. Two massive plates colliding, one diving beneath the other. Enormous amounts of energy stored as the plates lock against each other, then released all at once. When a large earthquake occurs along the trench, the displacement of the seafloor can push an enormous volume of water upward. That water has to go somewhere. It radiates outward in all directions as a series of waves that travel across the entire Pacific Ocean at speeds exceeding 500 miles per hour. In the open ocean, these waves are barely noticeable. They might raise the water level by only a few inches across hundreds of miles. A ship floating on top would not feel anything unusual. But when those waves reach shallow coastline, they slow down, compress, and build in height. A wave that was invisible in the deep ocean becomes a wall of water at the shore. This is a tsunami. The Pacific Ocean is ringed by subduction zones. The entire western edge, from the Aleutian Islands down through Japan, the Philippines, and New Zealand, is lined with trenches where plates collide. This network is sometimes called the Ring of Fire because of the volcanoes and earthquakes it produces. The Mariana Trench sits within this ring, contributing to the seismic activity that affects hundreds of millions of people living on Pacific coastlines. Monitoring these earthquakes is a constant effort involving multiple nations. Networks of seismometers and ocean floor pressure sensors are deployed across the Pacific to detect sudden changes in water pressure that indicate a tsunami is forming. Satellite systems relay the data in real time to warning centers located on coastlines across the Pacific Rim. When a large earthquake is detected near a trench, warnings are issued to coastal communities within minutes. In some cases, those minutes are all the time people have. The speed of response can mean the difference between evacuation and catastrophe. The hydrophone recordings made at the bottom of Challenger Deep captured the sound of these earthquakes directly. Deep rumbles and sharp jolts from tectonic activity both near and far were among the most prominent sounds on the recordings. The trench is not a quiet place. It is vibrating with the raw energy of the Earth rearranging itself beneath the ocean floor. And yet, life at the bottom of the trench appears undisturbed by the constant seismic activity. Amphipods scavenge, snailfish glide, tube worms filter. The organisms that live there have existed alongside earthquakes for millions of years. It is simply part of their environment. The violence of the Earth's interior is, for them, background noise. The earthquakes are a reminder that the Mariana Trench is not a static feature. It is an active, evolving boundary between two of the largest structures on the planet. And despite everything we have learned about it, we have barely scratched its true extent. Here is a fact that should unsettle you. We have better maps of the surface of Mars than we do of our own ocean floor. The entire surface of the Moon has been mapped to a resolution of about 7 feet. The surface of Mars has been mapped to a resolution of about 20 feet. The floor of Earth's oceans, on average, has been mapped to a resolution of roughly 5,000 feet. That means there are features the size of skyscrapers on the ocean floor that we do not know exist. As of recent estimates, less than 25% of the global ocean floor has been mapped with modern high-resolution sonar. The rest is filled in with rough estimates based on satellite gravity data, which can detect large features like underwater mountains and trenches, but cannot see anything smaller. The Mariana Trench itself has been partially mapped by sonar surveys over the past several decades. The general shape is known. The approximate depth of Challenger Deep has been measured repeatedly with increasing precision. But the fine details, the small canyons, the ridges, the individual vent sites, the slopes of the trench walls, the composition of the sediment in different zones, all of it remains largely unknown. Scientists working on the trench often compare their situation to trying to understand an entire continent by looking at a few photographs taken from a plane at night. Consider the scale. The trench stretches over 1,580 miles. Its average width is 43 miles. The total area of the trench and its immediate surroundings covers tens of thousands of square miles of seafloor. Of that area, human cameras and remotely operated vehicles have directly observed a tiny fraction. Estimates vary, but some scientists suggest that less than 1% of the trench floor has been seen in any meaningful detail at all. We are making decisions about the deep ocean based on glimpses. Every expedition to the trench has found something new. Every time a camera reaches a new spot on the floor, it captures species, geological features, or chemical processes that were previously unknown. the rate of discovery is not slowing down. If anything, it is accelerating as technology improves. The Hadal Ecosystem Studies Program, the 5 Deeps expedition, the Chinese Striver, missions, each returned with significant new findings from the small areas they explored. Extrapolating from those results across the vast unexplored regions of the trench suggests that what we know is a fraction of what is there. This lack of mapping and direct observation is not limited to the Mariana Trench. It applies to the entire deep ocean. Scientists estimate that over 70% of the Earth's surface is covered by ocean, and the average depth of that ocean is about 12,100 feet. The volume of habitable space in the deep ocean dwarfs the habitable space on land, and most of it is unmapped, unvisited, and unstudied. A 2024 study estimated that humans have directly observed only about 0.001% of the deep sea floor. That is not a typo. We have seen less than 1,000th of 1% of the deep ocean bottom. That number puts everything we know about the Mariana Trench in sobering context. The creatures we have found, the geological features we have documented, the ecosystems we have described, all of it comes from an almost impossibly small sample of the whole. The true scale and diversity of what lives in the deep remains completely unknown. And yet, even with so little explored, the deep ocean has already revealed things that rewrote textbooks. What else is waiting in the 99.999% we have never seen? Before we confront that question, there is one more comparison that puts the trench's isolation into perspective. A comparison with outer space. As of recent counts, over 600 people have traveled to space. 12 people have walked on the surface of the moon. The International Space Station has hosted hundreds of astronauts over its operational lifetime. Space travel, once considered the ultimate frontier, has become routine enough that private companies now sell tickets. Fewer than 30 people have reached the bottom of the Mariana Trench. This number is accurate. From the first dive by Pickard and Walsh in 1960 through the most recent descents, the total count of humans who have touched the deepest point on Earth remains under 30. Some counts place it closer to 20, depending on whether all dives to Challenger Deep specifically are included. The contrast is striking. We have sent more humans off the planet entirely than to the deepest point on our own world. The bottom of the ocean, just 7 miles away, is more exclusive than orbit. The reasons are not entirely about difficulty, though the technical challenges are severe. A spacecraft must survive a vacuum, radiation, and extreme temperature swings. A deep-sea submersible must survive pressure over 1,000 times greater than its sea level, corrosive salt water, and complete darkness. Both environments are hostile, but the engineering challenges are different. In some ways, the deep ocean is harder. A crack in a spacecraft hull in orbit gives you minutes to respond. A crack in a submersible hole at the bottom of the Mariana Trench gives you nothing. The implosion would happen faster than your brain could process it. The real reason for the gap is attention. Space captured the public imagination during the Cold War and has kept it ever since. Movies, television shows, news coverage, and government programs have maintained a deep cultural fascination with the stars for over 60 years. The deep ocean, by comparison, gets a fraction of the media attention and a fraction of the research funding. The budget of the National Aeronautics and Space Administration is roughly $25 billion per year. The budget of the National Oceanic and Atmospheric Administration, the primary agency responsible for ocean exploration in the United States, is a fraction of that. Globally, ocean research funding is dwarfed by space research funding. The disparity shapes what gets explored and what does not. There is also a visibility problem. Space is photogenic. Rocket launches are dramatic. Images from the Hubble telescope and Mars rovers generate worldwide excitement. The deep ocean is dark. Footage from submersibles shows murky water, dim lights, and strange creatures that many people find more unsettling than inspiring. It is harder to build public enthusiasm for a place you cannot see. But the scientific value of deep ocean exploration is enormous. The deep sea contains the largest biosphere on Earth. It regulates global climate through carbon cycling. It hosts ecosystems that could teach us how life survives in extreme conditions. It contains mineral resources that industries are already eyeing for extraction. Understanding it is not optional. It is essential. And the trench has a direct connection to one of the most ambitious scientific goals of the current century: the search for life beyond Earth. The environments found at the bottom of the Mariana Trench, the hydrothermal vents, the cold seeps, the chemosynthetic ecosystems are the closest analogues we have to conditions on ocean worlds in our own solar system. Studying them does not just teach us about Earth. It prepares us to recognize life when we find it somewhere else. Every organism discovered in the trench expands our understanding of what is biologically possible. Every vent community mapped gives astrobiologists a new model for how life might exist on a frozen moon with a hidden ocean. The Mariana Trench is not just a record holder for depth. It is a research site with implications that reach beyond our planet. And the worlds it most closely resembles are closer than you might think. Beneath the frozen crust of Jupiter's moon Europa, there is an ocean. Not a small underground lake. A global ocean of liquid salt water stretching across the entire moon, estimated to hold roughly twice as much water as all of Earth's oceans combined. This ocean has never been seen directly. Scientists know it exists because of the way Europa behaves. The moon flexes and deforms as Jupiter's immense gravity tugs on it, and the pattern of that flexing only makes sense if a liquid layer sits between the rocky interior and the icy shell above. Magnetic field measurements from passing spacecraft confirm the presence of a conducting fluid beneath the ice. Salt water fits the data. Europa's ocean sits in total darkness, sealed beneath miles of ice, under immense pressure. No sunlight reaches it. The temperature is frigid. The only potential energy sources are chemical reactions between the ocean water and the rocky seafloor below. That description should sound familiar. It is almost identical to the conditions found at the bottom of the Mariana Trench. Hydrothermal vents on Europa's seafloor, if they exist, could produce the same chemicals that power chemosynthetic life on Earth. Hydrogen sulfide, methane, hydrogen, the ingredients that bacteria in the Mariana Trench use to build food chains in total darkness. If those chemicals are present on Europa, and the geology strongly suggests they could be, then the same type of life could theoretically arise there. Saturn's moon Enceladus offers an even more tantalizing case. In 2005, the Cassini spacecraft flew past Enceladus and photographed enormous plumes of water vapor and ice particles erupting from cracks in the moon's south pole. The plumes were shooting hundreds of miles into space, visible against the blackness, a moon venting its ocean into the vacuum. Later analysis of those plumes found they contained sodium chloride, common salt, along with organic molecules and molecular hydrogen. The hydrogen is especially significant. On Earth, hydrogen in hydrothermal vent fluid is a primary energy source for chemosynthetic microbes. Finding hydrogen in Enceladus's plumes suggests that similar chemical reactions may be happening on its ocean floor right now. Scientists cannot yet confirm that life exists on Europa or Enceladus. No probe has been sent to look directly. But the Mariana Trench gives them something almost as valuable: a living example of what those alien oceans might produce. Every chemosynthetic bacterium found in the trench is proof that life does not require the sun. Every tube worm colony thriving at Hadal depths proves that complex organisms can survive extreme pressure and total darkness. Every vent community documented near the Mariana Islands adds detail to the blueprint that astrobiologists will use when they finally send instruments to these distant moons. NASA's Europa Clipper mission, launched in 2024, is designed to study Europa's ocean from orbit. It will map the ice shell, measure its thickness, and search for areas where ocean water may be reaching the surface. Future missions may attempt to land on the ice and eventually melt through it to reach the water below. When those instruments reach Europa's ocean, the scientists interpreting the data will be drawing directly on what we have learned from the deepest places on Earth. The Mariana Trench is the training ground. The connection between the trench and the search for alien life is not a metaphor or a loose analogy. It is a direct scientific pipeline. The same researchers who study chemosynthesis in the deep ocean contribute to mission design for planetary exploration. The same chemical signatures they measure at trench vents are programmed into the instruments that will scan for life on other worlds. The deepest place on Earth may ultimately end up being the key that unlocks the discovery of life beyond it. But even with all of this knowledge, all of these expeditions, all of these discoveries, one fact remains that is perhaps the most unsettling of all. We have sent submersibles to the bottom. We have recorded its sounds. We have pulled creatures from its depths and found plastic in their bodies. We have mapped its shape with sonar, measured its pressure with sensors, and photographed a tiny fraction of its floor with cameras attached to robots. And we still know almost nothing about the Mariana Trench. That statement is not an exaggeration. The trench stretches for over 1,580 miles through the Western Pacific. Its total area, including the slopes and surrounding features, covers tens of thousands of square miles. The number of dives that have reached its deepest points can be counted on two hands. The total area directly observed by cameras represents a speck so small it barely registers as a percentage. Every expedition that has visited the trench has returned with surprises. Picard and Walsh saw life where none was expected. Cameron found a barren landscape that contradicted assumptions about deep-sea biodiversity. Vescovo found plastic where scientists hoped nothing human had reached. The Striver found thriving colonies of large animals where models predicted only sparse microbial life. The pattern is unmistakable. Every time we look, we find something we did not predict. And we have barely looked at all. The trench contains features we know about but have never explored. The Sirena Deep, the second deepest canyon on the planet at over 35,400 feet, has been visited only once. Dozens of seamounts, ridges, and secondary canyons along the trench have never been seen by any camera or human eye. Entire sections of the trench wall, miles of vertical rock face descending from the upper ocean to the Hadal Zone, have never been surveyed in detail. The mud volcanoes have been mapped from above but rarely visited at close range. The hydrothermal vents discovered along the back arc have been explored during a handful of expeditions, with scientists finding new vent sites nearly every time they search. The cold seeps that support the tube worm and clam colonies found by the Striver are known from only a few locations. The trench floor between those known sites is uncharted, and then there are the things we cannot even predict. Every major deep-sea expedition in the past 2 decades has discovered species completely new to science. Not variations of known animals, entirely new organisms with body structures, survival strategies, and biological chemistry that had never been documented. The translucent snailfish, the ghost octopus, the metal-armored amphipods, each one was a surprise. If the rate of discovery stays consistent, the Mariana Trench could contain hundreds or even thousands of species that no one has ever seen. Some scientists believe the deep ocean as a whole may hold millions of undiscovered species. The trench, as the most extreme deep ocean environment on Earth, is almost certainly home to organisms uniquely adapted to its conditions. Organisms that exist nowhere else. There is also the question of what lies beneath the trench floor. The cold seeps and mud volcanoes prove that fluids and organisms from deep within the Earth's crust can reach the seafloor. How deep does life extend? Into the rock below? Some studies have found microbes living miles beneath the ocean floor, surviving in cracks and pores in the rock, feeding on chemical reactions in conditions that were thought to be sterile. The Mariana Trench may not just be the deepest place in the ocean, it may be the gateway to life extending deep into the planet itself. We have scratched a thin line across the surface of the deepest place on Earth, and found more mysteries than answers. The trench does not reveal itself easily. It guards its secrets behind crushing pressure, freezing darkness, and distances that our technology can only barely reach. But every dive goes a little further. Every expedition brings back something that changes what we know. The trench is patient. It has been waiting for 170 million years. We have only just started listening.